All right, now I got the feedback.
Steffi?
Yes. Should I start?
You can begin, yes.
Okay, great. It's really weird to talk to this computer without any feedback. Okay, great. So yeah, I will start this session. Thanks to Marilyn to give me, and the entire team to give me the opportunity to present here. I'm Stephanie Arndt from the Alfred Wegener Institute here in Bremerhaven in Germany. And I present today pretty recent work on the sea ice growth from the top in the Weddell Sea, based on observations of meteoric and snow on sea ice in the northwestern Weddell. So having at first a look in general on the Antarctic sea ice and snow cover, we all know that we have the kind of maximum sea ice extent in September, here shown for the year 2018, where we reached the maximum of about 18 million square kilometers. And then when it comes to summer, most of the sea ice is gone, whereas only 2 to 3 million square kilometers of sea ice are left. And those are basically, or big parts of that are sitting in the end in the northwestern Weddell Sea. Also having a look on the snow distribution on the right, derived from ISAT data from Stefan Kern and Borschu. You can also see here that, of course, also given the fact that we have those leftovers of sea ice in the Weddell, also in the northwestern Weddell, this is also the area where we have the thickest snow both in winter and in spring. And due to the fact that we have that persistent snow cover on the Antarctic sea ice, we have also two major effects determining actually the surface properties or the snow properties. On the one, we have during winter and spring, due to the fact that we have the thick snow layer on top of the sea ice, this might cause the snow sea ice interface to go below the water level, leading to the fact that we have flooding of the snow ice interface. This flooded area is refreezing, and during those refreezing, new ice is forming, and this is so-called snow ice. On the other hand, during summer, when it's getting warmer, but it's not getting as warm as that the entire snow could melt, but what we do observe in Antarctica are those temporary snow melt events, leading or snow melt and then refreeze events, leading to the fact that we have compaction of the snow layer, but also internal snow metamorphism processes. In addition to that, we have that superimposed ice is a pure fresh layer, while snow ice is a pure is a salty layer as the sea ice itself. So therefore, knowing those two mechanisms, the leading science question in that talk is that we want to quantify those ice growth processes from the top by in situ observations, and those were done, as mentioned already, in the northwestern Weddell. The expedition I'm here referring to is the so-called PS 118. It was a Polarstern expedition last February till April. And the sea ice, or no, not the last, so in 2019, the project was called Wet Ice. And as part of Wet Ice, we managed to conduct 15 ice stations. Those are marked here in the red dots. And in addition, we did quite some intensive EM bird flight programs. This is shown in the black lines, which allowed to measure the sea ice thickness. We did, in addition, on all these ice stations, a lot of sea ice coring. We did a lot of sea ice and snow thickness transects. And the sea ice coring was not only for physical. This is actually, I will concentrate now for that. So as I said, so we did on the one hand the EM bird flights, showing here the thickness range in the left panel. And then on the middle and on the right panel, we see the ground-based measure from the total sea ice thickness from the ground measurements, and from the airborne ones. They look pretty, so they are kind of in a similar range. So therefore, the flows we picked were representative for the area. And so we came up all together with a mean total sea ice thickness of about 2.34 meters, while we had a mean snow depth of about 26 centimeters. However, knowing these values, we know from previous expedition to the northwestern Weddell Sea during wintertime, in 2013, the expedition AVEX, and in 2006, the Weber's expedition, we observed snow buoys drifting through the Weddell Sea. We know that we have all over an annual snow accumulation rate of about 90 centimeters. And those are, of course, quite in contrast to those observed 26 centimeters now only during wet ice. And of course, you might want to have a look a little bit more in detail, what is now really the impact of the snow ice and superimposed ice. So at first, of course, starting from the top, we did on those ice stations also quite intense snow programs. So did a lot of snow pits, and also did measurements with a snow micropen. So really measuring the snow depth through the snow density through the entire profile. And what we saw from those results in those measurements is that we had about 60% of all sampled snow grains were actually already melt forms. So as I said, the expedition took place in February till March. So this was already kind of the end of the melt season. And this is really what was the snowpack characterized. And of course, when this is already part of the snowpack, it's even more interesting to see what is the ice cover looking beneath like. So therefore, we did a quite intense ice core program. We therefore took ice cores, as I said, for a bunch of biological parameters, but for the sea ice physics, we took samples for salinity, and those samples then also were measured for isotopes. And we also did before, already on board the ship, 6 sections to get an idea of the texture of the ice cores. So this is here now an example for an ice core with a total length of 2.12 meters, a snow depth of about 15 centimeters, and the total freeboard was about 30 centimeters. And going now, and then, so what you see here now in red are the isotopes, in blue, in black are the salinity measurements, and in blue the deuterium. And now to distinguish based on those measurements, superimposed ice and snow ice, we use those two criteria as shown here on the right. So when the isotopes were actually lower than 0.35 per mil, and the salinity smaller than 0.2, then we called it superimposed ice. And for higher salinities, it's actually then snow ice. And of course, when the isotopes are higher than those 0.35, then it's basically pure sea ice. And now going through that example of a section here, we see here that part of the core. This is what we analyzed in the end as superimposed ice of about 10 centimeters. And then the lower part of about 14 centimeters, we observed the snow ice thickness. And those analyses we did then for every single ice core we took all over. It has been 21 cores. And this is what we get all over on the right now, again, the graph with all measured salinity and isotopic measurements and color-coded for snow, superimposed ice, and snow ice that was determined by those criteria. And then we get all over superimposed ice thickness of a mean value of about 11 centimeters, ranging from 0 to 35 centimeters, and for snow ice, an average of 21 centimeters, ranging from 0 to 93 centimeters. Well, this is, of course, it sounded then when having a look on that, it looked really, really big. So therefore we thought, okay, when we now sampled those ice flows, it's of course also interesting to see where did those ice flows came from that we sampled. Therefore, Thomas Kumpen from ABI, he has an ice tracking algorithm and tracked those flows back. And they basically all came from the Flichner-Ronny area. And they were supposed to last, or that it seems like that they all took about a year. So the color code in the right panel shows like when they have been in which area. Based on that, I used a really simple two-layer thermodynamical sea ice model, and that revealed for that seasonal ice flows and along that track roughly sea ice thickness at the end. When we have been in the area where we sampled, the ice should have had an ice thickness between 1.5 and 1.8 meters. However, this is not what we observed because we had a range in the sea ice thickness from like 0.6 to more than 3 meters. Therefore, we characterized all ice flows we sampled in two categories. On the one hand, the really first year ice ranging between those 1.5 and 1.8 meters. And then everything what was significantly below those 1.5 meters was characterized as young first year ice, and everything that was above 1.8 meters was then characterized as second year ice.
Steffi, you have 5 more minutes.
Mm-hmm. Based on that, yeah, I did the same analyze again. And we see here now separated the salinity and the isotope analysis for the three groups I just mentioned before. And having now in the right panel and in the right table an overview on the superimposed ice and snow ice fractions, it looks actually much more reasonable. So we have now, especially when we exclude those young first year ice sessions, meaning that this is really ice where we expect that it's either a refrozen lead that formed during the drift upward, northward, or when it's basically because we couldn't track all ice flows, but most of them. But we guess that also parts of the ice flows were just built in the inside basically of the Antarctic Peninsula, so therefore did not have such a long travel. And therefore we see then, for example, now for the snow ice, we see for the first year ice an average of 18 centimeters, and for the second year ice an average of 10 centimeters. Comparing now those values to observations from earlier years. First of all, to the superimposed ice, we see, as I said, for the first year ice 11 centimeters, and for the second year ice 17 centimeters. Whereas when we compare that to an expedition here from the 1997, we do see only 8 centimeters. So obviously the superimposed ice fraction increased. And comparing then also the snow ice fraction to earlier observations, again, it's only kind of useful to compare it also to the Western Weddell, to the second year ice. And here it seems actually that it's in a similar range of about 4 to 5% of the ice cores, of the single ice core. So putting all these together brings me to my take-home message. So we saw that the snow stratigraphy indicates really basically the melt freeze forms as a prevalent snow grain type in the late summer snowpack, what we actually also expected beforehand. We saw also that the seasonal fate of the Antarctic snowpack is basically driven by the significant transition into meteoric ice. So all the snow that we observed during the winter expeditions is basically transformed into snow ice and into superimposed ice. And when we compare now those results to previous campaigns, we do see the higher proportion of the ice growth in general on top, as we have those higher superimposed ice fractions. And this has, of course, a positive contribution to the sea ice mass budget, as we have now less snow and therefore less ice insulating properties, and therefore more heat can be transferred. And so this is kind of, allows to grow more sea ice and less melt in summer. And on the other hand, we hypothesize, due to the fact that we have this higher proportion of the superimposed ice, which gives indications of an increasing snow melt, we propose that there's a potential onset of a so-called arctification of the Antarctic sea ice in the vicinity of the Antarctic Peninsula. So that is the region where we also do not only see in the sea ice, but also in general in other records that we see in general warming and change also due to the climate change. Yes, and with that, I come to the end, and I thank for your attention, and I'm happy to take questions.
Thank you very much, Steffi. There are two questions, one from Will Hobbs and one from Rob Massam, and also a third now popped in from Steve Ackley. Will, do you want to go ahead and read your question to Steffi?
Yeah, sure. So I guess I'm very interested in that spread that you get in salinity in the snow ice in your profile, Steffi. And I'm interested in the implications that has for brine rejection and ocean sea ice interactions. Do you know what the source of that spread is? Why it's so much higher than pure sea ice?
In the snow ice, you mean?
Yes, that's right.
Well, I mean, it's basically, I think, driven in general by when the snow is falling on the ice, and therefore when it gets flooded. And then I think it's also in the end kind of equation of the temperature. So how fast does the snow ice freeze again, so that you have then that the salt can either again kind of percolate downward, or it's just like freezing pretty soon. I think this might be one reason how in the end you have, or why you have in the end the spread in the vertical salinity profile in the snow ice, especially. Okay,
great. Thank you, Steffi.
And Rob?
Oh, hi, Steffi. Thanks very much. A great talk. Thank you. I was just wondering, in our work, we've tended to see quite a lot of thaw freeze in spring and winter as well, as storms move across, particularly at maximum extent. So the ice is quite low latitude at that time. Is that something that you've encountered too?
Well, so not in that study actually. So because as you have seen, so along the when you look at the trajectories, it's really, I mean, during spring, summer, it would have been like really far south. And therefore, there it's really that is what we know, that it's really super cold there. And this also from the snow buoys, we did not record there so far a real, summer or like a real warm air intrusion during spring and winter times actually. So therefore, I cannot comment on that for at least not for that region.
Yeah, thank you, Steffi.
And a final quick question from Steve Ackley.
Yeah, Steffi, I was wondering if the ice core pits were flooded at the time of sampling.
Yes, so we observed quite often in a flooding of the a flooding when we did the drilling. So therefore, we tried, of course, to be as efficient as possible in the field to make sure that we have not pollute the ice core with the flooded stuff. But yeah, so it was really the negative freeboard was pretty often observed.
Did you count that as part of the snow depth?
No, so we called really here only the snow depth, the stuff where we could still stick through, and where you still could see in the end the kind of the snow grains. Also, when we did then the 6 sections in the cold lab.
Do you know how deep those flooded layers were? Would they vary a lot, or did you see them?
Oh, I would need to go through the data. So we have, of course, yeah, I don't have it in mind here. I would need to look that up, sorry.
Okay.
Okay, thank you for those questions. Steffi, thank you for a really excellent start to our session. If you will unshare your screen and allow the Gunther, I think it is, to share his for the second talk.
Okay. Okay. Good evening, everybody. So my presentation is about the detection of sea ice leads from thermal infrared satellite data. And the most of the work was done by Fabian Reiser from our team. And the project was funded by the German Research Foundation. So sea ice leads are cracks in the ice. This view from an aircraft gives the impression this lead is approximately 2 kilometers in width, but many kilometers in length. And sea ice leads is thin ice in open water, and it transfers a lot of energy to the atmosphere, as you see in the formation of clouds by latent heat release. So the reason for the formation is mechanical forcing, mainly ocean currents and wind stress. And as said before, the impact is on the sea ice ocean atmosphere system via the release of sensible latent heat, but also sea ice formation and dense water formation. So our work is done with infrared satellite data, and we are using MODIS data from the last 17 years. Use the temperature data, and you see here the signature of leads here in a swath of the MODIS infrared data. You see the warm signature in the surface temperature. But the problem is that there are also sometimes clouds which are disturbing the image. In the end, so we have data about 1 kilometer resolution at nadir. So the algorithm conceptual scheme is shown here. So we're using all the available data of the infrared imagery. We're taking the temperature-based texture-based techniques to detect leads, and also additional parameters we'll show in a minute. It gives them daily composites of leads for the winter period. We have the time for the Arctic and also for the Antarctic. I'm only talking about the Antarctic here. And after that, we use a fuzzy filtering to select or to discriminate clouds and providing lead scores. In the end, we have a final product. We have the manual control and giving some uncertainty to the product. Okay, so what you see in here is a snapshot for one day in May 2016, showing the map of where we have sea ice. Then we take as background MSR, sea ice coverage, and then the MODIS potential leads, which means potential lead counts. To zoom in for Weddell Sea, which I will focus here on, we see how often we have leads detected by warm signatures, and you see that even that where we many counts per day, then it is quite some certainty that we have really a lead here. There's also a scheme how that works then all together to generate lead score. So we use a potential open water concentration, sometimes a clear sky fraction, how many observations we have per day from available observations, and then derived leads, predicted leads, and further parameters, combine them, and that's like a little bit in the fuzzy scheme like a neural network combine them with rules, and then in the end we come up with a lead score. So as an example, we see here again an image with a ice surface temperature. We see the warm signatures here. From those produce a lab of binary map of potential leads here. See leads, no leads. And then we go further. We use this potential open water, so some kind of CS concentration algorithm to have a available or CS concentration, or the 1 minus CS concentration to be exactly. Then we make an edge detection, so which is shows sharp contrast between warm and colder signatures. And then we look if the feature is linear, which we expect for a lead, linearity score, and then we have combined the two predicted leads here. So, and this is now the lead score, or the final product, which shows us again the same image as before, but now to move it, we have some uncertainty or certainty if the lead available here in this region. You see the yellow, we have a highest lead score. Then we have areas where sea ice, the background again is the AMSR, but only dark colors, which are low lead score. That can be also cloud artifacts. So then we come to the a histogram here, which shows for the same day here. If we plot the lead score in bins here, we see we found that 30 value of 30 for the lead score is good to discriminate artifacts from potential leads. And then the distribution goes here to about 15. And then we have now the manual element here that we took 6 lead score maps and then make a manual quality control. So about 10 persons did that independently. That was then combined, and then we can attribute the lead score to uncertainty, but a manual quality control, and you see it's quite a good relation here. And we were also really surprised that it's that good here. So in the end, we come up for the same day now with a pixel-wise uncertainty here. So we can have the clouds in black. We have also other artifacts we are not sure. And then we have the a very high certainty and then going to lower certainty with the yellow colors. Again, you could look at the detail here. You see the green is very good and yellow is worse, but it's still a high some probability that there's a real elite. So what I'm showing here is now the result. So we come up with a daily lead maps and then combine it to climatology now from 2003 to 2019. And what is shown here is only a lead score exceeding 30%, where we say that we can quite sure there is a real elite. And then we come out here with this map here, this distribution. And when we did that first, it was rather striking. So see this linear feature here in the map here. And then combining that with a bathymetry here and flipping forth and back, you can see that very nicely we get the high lead frequency, these lines along the shelf break here. So that was quite interesting that we find a nice relation of the lead frequency with the bathymetry of the ocean. To look at more detail for the Weddell Sea and Ross Sea area, you see this line here, and compared by the bathymetry, we see it's exactly the shelf break here. And it's also in other regions, like here in the Ross Sea, where we see with agreement. we can look at that in more detail, taking a cross section here in the Antarctic Peninsula to the deeper ocean. And that's a gray line here. Along this cross section is the bathymetry, ocean depth. And then in red is the frequency of leads. This we see close to the coastline, one peak which is associated with the coastal polynyas, which also are seen here. When they form, they may also fit the criterion of a lead when they are quite small. So we see it also in the data. But the second peak here is then exactly where we have the shelf break and this change in the topography. So we, colleague of us in Paris, run a CS ocean model, NEMO, also to simulate the surfing current, and we analyzed the divergence of the flow field here at the surface. You see nicely, we can also follow here in red, we have the divergence, positive divergence. You see a line of divergence here along with a line of increased lead frequency. So for we find some relation also with ocean currents. So that are
you have approximately 5 more minutes.
So in summary, we have evaluated lead observations for the last 17 years, only the winter months. We have developed a robust lead retrieval algorithm based on the MODIS infrared data, and we can show that we find persistent lead patterns associated with bathymetry, not only what I discussed here, but also we see the mode rise and so on, also in the data. And so that's quite interesting also for the ocean scientists. So the material is published. We have 2 published papers recently, one month ago, and also the data published, so it can be downloaded freely in Paglia database. Thank you very much.
Thank you, Gunther. There's time for a couple of questions. I have one.
Yeah.
Normally, I think about sea ice leads opening and closing in response to wind, surface wind. How does that fit into the picture that you just painted there? Because I think you're suggesting that it's more associated with it is associated also with the bathymetry.
Yeah, we have also lead frequencies everywhere. So with the winds, they are not at the same position. So they're just drifting, and that is smoothed out here. For instantaneous image that I showed before, you see also the leads here. Mm-hmm. But they are moving, and you averages over a long time, you don't see the individual leads anymore. You see some frequency, as in the climatology, again, back to here. You see we have here sometimes of 10% of the time we have leads here in this area, but we see only this very consistent picture here with the bathymetry.
Mm-hmm. Okay, thank you. There are a couple, there's 3 other questions in the chat. I'll just, Alex, can you have that question, ask a question quickly?
Sure. So I found working with Mod 3.5, the cloud mask product, that some of these leads were falsely detected as thin cloud, or maybe it wasn't falsely, maybe it was just the cloud, thin cloud that's just evaporated sitting on top of the lead, and then we couldn't see the leads because they were masked out. Do you have that problem with the Mod 2.9 data?
Yeah, so that's the issue that that the cloud mask available with the mod data, but we have too many errors in the cloud mask. So that's why we do all this algorithm here to filter out the clouds.
Okay, but doesn't Mod 29 use the cloud mask? Does it try to estimate ice surface temperature even where Mod 35 says there is a cloud?
No. So we don't use it. So we only use Mod 29 when there is no clouds.
Okay, got it. Thanks.
Okay, there are several other questions in the chat. Gunther, can I direct you to go to the chat when you've unshared your screen and respond to those questions? Please. And can you release the screen and have our third speaker share his screen?
Okay.
And Ryan, thank you very much. You may begin.
Can you see my screen okay?
Yes.
Okay. Yeah, thank you to the session organizers for allowing me to speak about some early but I think exciting work that we're doing here with my grad student Amanda on an NSF-sponsored project. Here I'll be talking about Antarctic sea ice extent reconstructions during the 20th century. So I don't have to really talk to this community quite a bit about how exciting sea ice news is. And this is a paper that just came out about a month ago talking about the Weddell Sea and the changes there in 2016 and some potential causes for those changes. And this, of course, made headlines all around the world. This is just the New York Times showing you this paper in the press release. And so sea ice is really exciting. And you look at this time series of the Weddell there from 79 to 2015 during the period of a lot of satellite data. And you can see in the summer here in the top and in the fall, there are these statistically significant increases in sea ice extent in this region. In the winter and the spring, there are statistically insignificant changes. There are slight decreases in these periods. But then 2016 came along and the whole thing changed, right? So the sea ice dropped down markedly in the Weddell Sea in 2016 and it really hasn't rebounded since. But if you're like me, you look at this time series and it's really short. This is really the period of the best satellite measurements of sea ice extent. And there are a few earlier estimates of sea ice from satellite data. And, there's reconstructions from ice cores and maybe some limited measurements from ship logbooks, but there's not a lot of good data. And so you look at this and you're like a little sad, like what's going on in the early 20th century? And so this is where my work comes in. I want to know, can we actually give an estimate of what sea ice might have been like continuously throughout the early 20th century? So we're doing this by doing a method called principal component regression. And it's based on the relationships that there are with climate and sea ice extent across the southern hemisphere throughout the 20th century. And we're examining the reconstruction performance in three different ways. First, we're going to use multiple different data networks to check for stability. How sensitive is the reconstruction that we're getting to what data we're putting into it? We're also going to do an independent validation. Because the sea ice record is very short, it's only about 40 years now, we don't have a lot of data to withhold from our model when we calibrate it. So we're doing an independent validation approach by predicting 1 year at a time based on the fitting measures that we get. And we predict that year independently so that we withhold years around it so that it's not influenced by the measures of the model with the years beside it. And we're also currently ongoing work to do further validation with lots of different sources of independent data, including reconstructions from ice cores, logbooks from ships, and some early satellite measurements. And that's stuff that we're doing independent completely, and that's ongoing right now. We're reconstructing sea ice extent by sector, and so looking at sector averages sea ice extent, and we're doing this for 5 different sectors. These are based on the boundaries established by Raphael and Hobbs in 2014. They're slightly different than some earlier proposed boundaries. We're using the Raphael and Hobbs boundaries because they are a little bit more spatially discrete. So there's a little bit more difference between different regions in their sectors that they propose, and there's a more similar variability within a region. And so we're using 6 different sectors here. The King Haakon, East Antarctica, the Ross Sea sector, Amundsen-Bellingshausen Sea sector, the Weddell Sea, and then we're doing a reconstruction for total sea ice. And we're doing this for seasonal means. What kind of data are we feeding into our reconstructions to predict it? Our main data set is long-term temperature and pressure observations from across the southern hemisphere. And so here are 30 of those. This is our main data set. So these are very long continuous measurements that go back into the early 20th century. It also includes here number 28, which is Orcatus. Orcatus is the most continuous early record south of 60 South. It goes back to 1903. So it's a really great estimate for sea ice extent near the Antarctic Peninsula. And how are we doing this? We are examining relationships between this main data set with sea ice at various lags. So we'll look at the direct relationship at the same time for one season, and then we'll lag where the predictors, this temperature and pressure across the southern hemisphere, are leading the sea ice extent up to one season. We also examine various subsets of this data network. We don't use all 30 observations. We use only those that are significantly correlated with the Antarctic sea ice extent time series that we're trying to reconstruct. And that varies, of course, by season and by sector. So there's quite a bit different variations in the network that we're using. To ensure robust relationships among our data that we include, we also layer on, after using this observation data, indices of major modes of climate variability, such as INSO and the SAM, to ensure that we have robust relationships across our predictors. We're using a principal component analysis on these data sets so that we're not looking at individual stations, but rather the relationships among them. And we want to ensure by adding these data layers incrementally that we're capturing to some degree these really strong known modes of climate variability within a discrete, spatially discrete data set. So we're not also regressing all of the principal components onto the sea ice extent. We're using a subset of those. And by doing that, that removes unwanted noise in the data sets and makes the reconstruction represent how relationships between these individual variables influence the sea ice extent. And I think this is really how the real world works. It's not like pressure at Hobart that makes a strong influence on sea ice in the Ross Sea, for example. It's relationships across large sectors in space and time that influence sea ice extent. The data layers that we add on here beyond temperature and pressure, the climate mode indices are here in layers 2 through 10. So there are all these acronyms: the Interdecadal Pacific Oscillation, Atlantic Multi-Decadal Oscillation, Pacific Decadal Oscillation, Southern Oscillation Index, 4 Nino SST regions, and seasonal SAM index reconstructions that I have performed in previous work. So how are we doing? Well, here are 4 skill metrics of our reconstruction performance. They are the calibration correlation. This is simply just the correlation of our reconstruction with the observed sea ice during the period of overlap. The validation correlation is the correlation between our predicted fully independent validation time series with the observed sea ice during the period of overlap. That should be lower. It should not be as strong as the calibration correlation because it's predicted. And then there are the two other metrics here, the RE and the CE. These are comparisons of the mean. And so the RE compares the mean of the observed and reconstructed sea ice time series during the period of overlap. And the CE, coefficient of efficiency, compares the mean of the validation time series with the reconstruction during the period of overlap. For all of these skill metrics, what you need to know is that one is a perfect reconstruction. It matches exactly the observed data. And for an RE and a CE, any value greater than 0 indicates better skill than the climatological mean. Okay, now within these box plots here, this is because we're doing different data layers and different networks within the data, there's a possibility of up to 40 unique reconstructions per season in an Antarctic sea ice sector. When you multiply that by each box plot representing the 6 different sectors that we're reconstructing, there's a potential for 240 different reconstructions going into these measures, okay? And so this is the performance across all of those individual reconstructions. And what I can say is I'm excited that we actually can produce meaningful reconstructions. I wasn't sure going into this how it would work out, and I'm excited that, you know, in most all seasons, in all cases, we're getting skill values better than 0, which is, you know, the lowest bar I would have. And in fact, when we start breaking it down further, we're actually doing pretty good. And so one way that we can break it down is looking at our data networks. So there are 4 different networks here represented by colors. The 10% is the largest network across all of those predictors, and the 1% would be the most highly correlated stations at the significance level of 1%, and so it's a very small network in comparison. And what we see generally as the data network size decreases, the reconstruction skill also decreases. So the more data you give it, the more stable those relationships are across the different values, the data points, and the better the reconstructions are. When we filter to look at the best reconstruction in general, the one that has the highest measures of all these 4 statistics, this is what we have. So these box plots are now just over 6 different sectors per season. And so we can see that we now produce meaningful reconstructions. We're adding value to just the simple climatological mean, which is, how a lot of historical hat ice data sets, for example, are once you move beyond the satellite era. There's no, it's just the seasonal cycle that's related to the climatological mean. So I think our reconstructions are adding quite a bit of value there. And to show you that here's back to the Weddell Sea sea ice extent. This is the observed time series that I showed you at the beginning of this presentation. I'm happy now because we've added some value. So here in red is our best fit reconstruction, and the skill measures for those reconstructions are given in each plot up at the top. And then the blue is the ensemble average. So this is across the 40 different potentially unique reconstructions that we have. What's the average across those? The gray here represents a 95 uncertainty envelope. It considers the fit of the best performing reconstruction in red, as well as the spread of all the individual reconstructions that we produced. And so it gives you an idea of how confident we are going back into time about each individual value. It varies in time. And so the larger that gray shading is, the more uncertainty we have. The narrower it is, the more confidence we have in that particular value. And so I think we're doing pretty well here. These are correlated here in the Weddell Sea above 0.9 with the observed. And you're just using predictor values from the mid-latitudes. I haven't done a lot of analysis in detail about these reconstructions, but just to show you some things that you can see pretty quickly visually, in the summer and in the autumn, those low values that characterize 2016 and beyond seem to occur quite frequently in the early record there as well. And what I find personally exciting is that in the summer and maybe even in the fall, there's this slight negative trend in the best fit reconstruction, the red line, up until about 1960 or so. And my previous work with pressure reconstructions over Antarctica, trying to get a feel of what's going on with the large-scale atmospheric circulation, suggests that in the Weddell Sea in the South Atlantic, there have been really large pressure rises in the early 20th century that would characterize a negative phase of the southern annular mode and perhaps warming of the Antarctic continent that could be associated with some of these atmospheric drivers of lower sea ice extent in the Weddell Sea. Just to be transparent here, I'll show you one more quickly. This is the total sea ice extent. So this is a little bit less exciting, it's less skillful. I think it's still very exciting. It's just not as robust of a reconstruction perhaps as what we saw for the Weddell Sea. There's large variability here, both between the reconstructions and back into time. The summer here, for example, in total sea ice extent, you see quite large jumps in the observed, and our reconstruction suggests, at least the best fit one, that there's also similar jumps back into time. Again, I haven't done a lot of analysis on these, but that's ongoing with my grad students, and we hope to know a lot more about how unique these recent changes we have are in context over the last century. So our reconstructions double that record and I think add some new value. So just to wrap it up here and take some questions, I'm excited. I think we can produce meaningful seasonal sea ice extent reconstructions. This is for all Antarctic sectors and all seasons, and adds a new value that really helps to place current changes in a much longer historical context. I didn't mention it directly here, but our group is also performing monthly reconstructions that go back to 1957. So a little bit higher temporal frequency. But the great thing about these 1957 reconstructions is that they include all the Antarctic data and also sub-Antarctic island data that's close to the sea ice edge in some seasons. And these monthly reconstructions are even performing higher, much more skillful than we have for our long-term reconstructions with seasonal resolution. So I'm excited about those and the potential that they have to add us at least 20 or so years of additional measurements of sea ice with monthly resolution. As I mentioned at the beginning, our future work includes extensive validation of these reconstructions. And Marilyn and her group at UCLA are also doing really exciting reconstructions with more sophisticated Bayesian type reconstruction modeling. So not linear methods, but this really exciting ensemble type prediction that we're going to compare with as well to see how well our reconstructions match up and what can we say more about early sea ice extent across Antarctica. With that, I will stop and take any questions that you may have. Thank you.
Thank you, Ryan. I was muted there. I'm, of course, really excited about the results that you're showing. There is a question from Will. Will, would you go ahead and ask?
Yeah, hi Ryan. This is really great for me to see as well. Looking at your plots at the end, I know you said you haven't done a whole lot of analysis yet, but it looks from the naked eye that there's slightly less variance in the reconstructions of before the 70s than there is in the time series post 70s. And I just wonder if you think, is that a plausible thing, or is that more likely to be that the reconstruction algorithm mutes some of the more extreme variances?
Yeah, it's a good question. So certainly in the ensemble, I mean, of course, there's less variance in our reconstruction because it's an average across many different members, and so it mutes the variance. Our best fit reconstructions, those red lines, actually in some cases have more variance than the observed data. I didn't show some here. We're still unpacking those to understand how robust and reliable they may be. So it really does depend. We don't always see less variance. The less variance that you see here in spring, for example, in the total sea ice extent, just a measure of that we're not doing as great of a job at reconstructing in general. And so it's harder to get total sea ice extent. That's a large hemispheric pattern that's influenced by many things. And so using what we're doing for predicting that at its extent, at the greatest extent in spring, tends to not capture that variability well. And therefore, there we have things that are kind of hovering closer to the climatological average and less variance when our reconstruction skill is lower. But in cases like this, where we have pretty good reconstruction skill, we have still quite a bit of variance in our best fit red line there.
Yeah, okay. Thanks, Ryan.
There's one other question, after which we move on. Aaron, would you like to read out your question?
Yep. I was just wondering if, for one, there's a publication out on this yet, and on the other, if you can also do reconstructions on much smaller areas, such as McMurdo Sound or other small areas.
So there will be a publication forthcoming. I'm still wanting to make sure that we have the most robust data set before I publish it. And we'll also, at that point, put the data on Figshare so that it's publicly accessible so that anyone can access it. The smaller you go down in spatial scales, the more difficult it becomes. So that's why I've done seasonal sectoral mean sea ice extents here, because chances are that you're going to have stronger relationships with the picture data sets that we're using. Once you move down in scale, then it becomes more challenging. And so I haven't performed any smaller scale reconstructions yet, but from my previous work in doing numerous reconstructions across Antarctica, the smaller in scale you go, or the higher frequency you go in time, the more challenging it becomes, and the less reliable your reconstructions tend to be.
Great, thank you.
Thank you.
Rob, I'll allow one more, and then we will move on to Jan's talk.
Oh, sorry, Marilyn, very quick. Hi, Ryan. Thank you very much. Very exciting stuff. Just wondering if there's a possibility that early explorers, whalers, etc., collected useful data for your purposes pre-1957?
Ryan?
I'm here. I lost Rob, though. I don't hear him.
Oh, sorry, Ryan. Can you hear me now?
I can, yes. I heard about earlier expeditions, but that's the end. I'm sorry.
Yes, I was just wondering if there's any useful data out there if you were to go to Scott Pole or anywhere and mine the archives regarding early explorers and whalers pre-1957.
Yeah, absolutely. There's a great information in logbooks. The challenge is that it's we're doing seasonal mean here, and so it's often hard to pair those up. That they're often just getting to the sea ice edge, and in some cases going into it, but it's like 1 day or 2 days where they have measurements, and to make that comparison with the seasonal mean, sectoral means, is a bit challenging. But we do plan to use as much of that information as we can to see how well it matches up with our reconstructions and the uncertainty about them.
Great, thank you, Ryan.
Thank you.
Okay, thank you, Ryan, for a really interesting talk. And we're down to our final speaker for this session, for this sub-session. Jan, will you go ahead and share your screen?
Thank you. I'll try to share my screen. Which I obviously haven't done before, so bear with me. Okay, here we go. And it turns out I can't.
Why?
Because the security settings of my computer. Bear with me. Oh, I need to quit Zoom now. My apologies. Maybe, Marilyn, you've got the talk. Maybe I can ask you to share the talk and I'll just talk to it that way. My apologies.
Okay, hold on a second. Let me find it. And now I will share my screen in this one.
That's it.
Mm-hmm.
Can you get that in full screen mode? Oh, never mind.
I think this will do it. That's my full screen.
Thank you, and my apologies again. I'm talking about the CS prediction network for the Southern Ocean. And it's not just me behind that project, it's obviously quite a few people, Francois Massonet from Belgium, Phil Reed and Will Hobbs from Hobart as well, and John Five and Cecilia Bitz. What we are trying to do is coordinating CS prediction for the Southern Ocean and allowing a platform to compare with each other and to actually open the discussion and spur the interest in there. We are standing with that on the shoulders of the CS prediction network for the Arctic Ocean, which started off as the CS Outlook and has already accumulated more than 10 years in research. But on the next slide, we show that we are driven by really one question, and that is how well do current prediction systems forecast the seasonal evolution of circumpolar and regional and Arctic sea ice. There's a teaser published or to be published in the Bulletin of the American Meteorological Society, which is due to be available any day now. We're looking only at 3 years of prediction exercises so far, but I think there's lots of potential. There's obviously one or maybe two major regions. One is to predict the climate and understand how it all works, and the other thing is really going into the operational business and predicting CS conditions for supporting ship operations. On the next slide, I just want to go briefly into what this CS prediction network is all about. We want to provide a focal point for seasonal outlooks and stir the debate and increase awareness of the need to predict Antarctic sea as well. We aim to provide news and information on the state of Antarctic sea ice. That didn't quite work so well so far, but that's mainly due to lots of technical limitations. And initially, the whole exercise was aligned with the year of polar prediction. I assume that everyone in the room is fully aware of what that was and why that was. And we thought it might be a useful thing to tap into the special observing periods of the year of polar predictions to establish a large validation data set against which we could actually validate the model forecasts. On the next slide, we want to motivate ourselves. I've said that before, sea ice is a major hindrance for ships operating in in polar waters, and therefore predicting where sea ice is and how sea ice behaves is crucial in allowing safe and efficient operations. We do have ice charts for the Antarctic, but they're only providing a kind of nowcast snapshot of the situation as it is, and we don't really know how it will evolve, other than the sea ice will melt in summer and it will freeze in winter. There is, however, some new scientific evidence, and I'm not delving into a great deal of detail, but just to name a few, Marika Holland has a great Nature Communications paper in 2017, where she basically says, or links the sea ice extent and the sea ice behavior in the Ross Sea with zonal winds in early October. So enhanced winds in enhanced zonal winds in October lead to an increased ice divergence in the region of the Ross Sea that reduces lower ice concentration, that reduces albedo, that enhances shortwave absorption, increases oceanic heat, and therefore delays the sea ice formation in that region. So that there's a mechanism, if you want, which should allow us to predict sea ice for that region. And more recently, Sylvain Marchi and co-workers from 2018 have found a re-emergence of Antarctic sea ice predictability by its links to deep ocean mixing in global climate models. So they propose a heat storage in the lower layers of the ocean, which resurfaces at a later stage and therefore allows for a bit of a predictability on sea ice. On the next slide, we'll continue with when we did that exercise. We were soliciting summer sea ice conditions. That is December, January, February, initially only during the YOP year of 2017 to 19. We have had 2 assessments of those summer seasons, and both of these assessments are available in the reports that we produced. They're available, and the DOI is on the screen. We're continuing the effort in research mode this year and hopefully beyond. There's absolutely no funding attached to this. We all do that in our spare time, but we're very confident and very excited about the prospects, and therefore we continue just in research mode. On the next slide, what did we get? How did we do it? Well, we didn't do much in the end. We solicited submissions, and I'll go into the details of what these submissions included in a minute. But we basically received for this past summer season 11 submissions, 4 statistical models, 6 coupled dynamical models, and 1 ocean sea ice dynamical model. And I've lost my train of thought, I'm sorry. Maybe we just go to the next slide then, and showing some of the results that we've received. Oh yes, here's my train back. We were asking for 3 different types of forecasts. Essentially, the circumantarctic sea ice area might not be the best geophysical variable to predict, but at least is a variable that is available circumantarctic on a daily basis from remote sensing data. So we have a validation data set. We also were asking for regional 10-degree pie, piece of the pie if you want, and lower resolution in terms of daily values rather than just the minimum Antarctic sea ice extent and when that will happen. So on the left chart, you can see the predictions as they arrived in late November and early December when we were asking for the predictions. The two black lines are included in this graph, which show the observational data. One is from NSIDC, and the other one is from the OC-SAF Ocean Sea Ice Satellite as applications facility. Two different independent data sets who have some differences but generally agree. And you can see that the model ensemble, all of the models together, they capture the evolution of the summer sea ice decline, but maybe none to a degree that it gives confidence in the forecasting. The entire ensemble of all the models together obviously includes the observed value, but there's a large spread in terms of value and timing. On the right-hand side, the timing of the minimum is shown in the dots, and again, the vertical black lines include the observational data sets, and depending on which data set you look, they have a slight shift in the timing of the minimum there. Again, it is obvious that there's not a great deal of accuracy, except for the NASA GFC, which hit the mark spot on, and the ECMWF had one ensemble as well, or two ensembles. On the next slide, some more results. We were also looking at the value of the February mean sea ice area, and again, we can see a large spread of the predicted values compared to the observational means. And just for context, on the right-hand side is the February Antarctic sea ice area from the satellite record so far. And Ryan just talked about the slope and the evolution. One more slide in terms of results. Oh no, concluding remarks. There you go. Sorry. Concluding remarks. Thank you. The multi-model ensemble includes the observed state, so that was a good thing, good start. The timing of the minimum is not well predicted. Surprisingly for us anyway, it was statistical contributions appear to outperform others, and we're currently investigating and trying to find out why that is and how that is. We're currently preparing another paper where we want to delve with the contributors into the details of their models and their model performance. And the last, and from my point of view, being an ICE service member these days, most important conclusion is that it's not yet operationally applicable. If you want to, feel free to have a go at the data set itself. It's all available on GitHub. The address is in the lower right corner there. And with that, I'll conclude and thank you for your presence, and again apologize for the technical hiccups.
Okay. Sorry, I can't somehow share my screen and look at the chat. Does anyone have questions that you wanted to ask Jan about this?
Marilyn, I don't see any questions in the chat.
Yeah. The question I had was the one you answered at the very end. Is I'm thinking of getting perhaps my students involved in something like this, and I see where to do a contact. So that was my question, and you answered it.
Yes, so we're continuing in research mode. We want to provide an open platform for people to compare their model results. We are not in the business of benchmarking anyone, and we're always keen to have as many diverse contributions as we can gather and get a better understanding about the state and fate of Antarctic sea ice.
Marilyn, Steve, can I ask a question?
Please.
Yeah, Jan, you mentioned about the timing of the minimum being a little off in these models, but do you have some problems with that because aren't you seeing advances in some area while you're retreating in other areas right around the minimum?
Yes, correct, Steve. If you look at the circumantarctic picture, you're missing lots and lots of the regional variability. So
yeah.
Having just one number as a predictor and as your measure of success against a model set is obviously not suitable from an operational point of view, or maybe even not from a climatological point of view. But it was just a starting point, really. So we want to kickstart that conversation. We want to have people thinking about how can we make use of what the models can do. And we agree that having one number totally misses regional variability, and there's lots of regional variability around Antarctica.
Yeah, I think this would be like in the high latitude embayments of the Ross and the Weddell Sea. You know, we're seeing seeing some advance while it's still retreating at the northern edges. So,
yeah. The reason why we're kind of keen on the timing is that the timing of the minimum also kind of sets the time limit for Antarctic shipping operations. So again, I'm coming from this operational background and point of view again. And if we can predict when the minimum, at least in an area, occurs, then we can tell ship operators, look, by then you should really make your way out of the CS unless you want to spend the winter in Antarctica.
Thanks, Jan.
Thank you.
Okay, thank you, Jan, and thank you everyone who tuned in and listened to the first third of our presentations today. We'll now take that break a little 6 minutes later. I very cleverly put that time in there because I knew we would run over with I wanted to give a chance for questions. So we'll take a break now and return to begin. The session will begin at 45. I don't know what time zone you're in, but at 15 minutes to the hour, the next speaker will begin talking. So you have approximately 15 minutes or so break.
Thanks, Marilyn.
Thank you.
In SCAR meeting. This presentation is mainly about the wind-driven sea ice changes and variabilities around the Antarctica and its potential impact on the subsurface temperature and the salinity. So this is long-lasting work, and hopefully it will appear in next maybe several months. So one of the main motivation of this study is that there are so many climate changes happen around the Antarctica in the past several decades, and these climate change might be linked to each other. So in atmosphere, during the past several decades, the West Antarctica and the peninsula experienced a rapid warming, which is associated with the atmospheric circulation changes, including both the deepened atmospheric low and the intensified southern angle mode. So the sea ice changes experienced two different periods. So before 2014, the sea ice has been increased. The sea ice extension has been increased slowly. So with a redistribution between Ross Sea and the Amazon and Bellingshausen seas. But after 2015, the sea ice extension decreased suddenly. Our work is mainly about the first part before 2015. And the land ice melting could be the most important or our most concerned changes. So the land ice melting around the West Antarctica, especially the Pine Glacier and the Fresh Glacier, has been significantly accelerated in the past several decades. And recently, the Totten Glacier, so the melting becomes faster. So these changes around Antarctica, they are not only asymmetric usually the strongest changes happen around the West Antarctica. For example, the strongest circulation changes it could be the deepened MC slope in the past 3 decades, and with the West Antarctic warming, and also the land ice melting around the West Antarctica is much faster than East Antarctica, which could be associated with the subsurface warming in the ocean. So some observational evidence show that the subsurface temperature and salinity has been increased significantly around the West Antarctica, but the trend might not be significant around the East Antarctica. And so meanwhile, the ocean circulation or the sea level changes and the sea ice changes, I think the strongest or most significant changes also have happened around the West Antarctica. So the question is that these zonally asymmetric changes or these strongest changes around the West Antarctica, are they related to each other? Is there any mechanism link these changes? So previous works show some evidence that the circulation, atmospheric circulation, can drive the ocean circulation and sea ice, and the subsurface temperature, subsurface ocean temperature could like contribute to the land ice melting, but we want more. So that's why we designed a very simple experiment. We just use the observed atmospheric changes during the past 3 decades. So from early 1990s to 2015 to drive the ocean and the sea ice models. And so the first row is the observed changes, the observed sea level and basically the circulation, ocean circulation changes, and the observed sea ice changes, and observed subsurface temperature and salinity changes. And so first we have so we use the atmospheric changes, basically the deepened MC slope, to drive the ocean model and sea ice model. So we can well simulate the sea level change. The north part of the Ross Sea, there's a lower sea level anomaly center associated with the clockwise circulation change. We can well simulate the sea ice distribution. And surprisingly, we can also well simulate the subsurface temperature changes. The warming around the West Antarctica and the salinity increase around the West Antarctica, they're much stronger than what happened around the East Antarctica. So we really want to know the mechanism. In particular, we want to know what is role of sea ice, what happened in the atmosphere, sea ice, ocean interaction. So what we did is that we inactivate the dynamic module of the sea ice model. So then in this simulation, so the sea ice extension can no longer be changed. So what happens is that when we drive the model with the observed atmospheric changes, we can still well simulate the sea level changes, meaning that the ocean circulation are basically the same in the atmosphere. The ocean circulation response are basically the same in the sea ice active simulation. But the subsurface temperature and salinity changes are totally different from what we observed and what we simulated in the sea ice active simulation. So we do no longer have subsurface temperature warming around the West Antarctica. So what is mechanism? We really care about what happened in the model or in the real world. I think the basic idea is like in Professor Gauss' papers, the brine rejections, because when sea ice form, it releases salt water, and when sea ice melt, it releases the fresh water. But their contribution to the ocean stratification are not symmetric. Because usually when sea ice form, that's during the cold season, like the Austral winter, the mixed layer are much deeper than the climate, like in average. So the salt water can sink to the subsurface or deeper layer. But when the sea ice melt during the warm season, the mixed layer is shallower. So usually the fresh water just covers the surface. So if you intensify the sea ice formation or if we intensify the sea ice melting, both two processes can intensify the stratification of the ocean. So here's what happened during our like experiment period. So during the Austral summer, the melting around the Weddell Sea has been intensified. But during the Austral winter, the sea ice formation around the Weddell Sea has also been intensified. And if we calculate the freshwater and saltwater flux between the sea ice and the ocean, we find during the cold season, during the during the warm season, during the Austral summer, the freshwater release from sea ice to the ocean model has been enhanced. And during Austral autumn and spring, the saltwater release from the sea ice to the ocean has also been intensified. So this process caused the intensification of the stratification around the Weddell Sea and Amazon Sea. The left two panels are the salinity changes in the model. So here is the above 100 meter, it becomes fresher, and below 150 meters, it becomes saltier. Meanwhile, we have two profiles, one across the Weddell Sea and one across the Amazon Sea. And we both found that the salinity over the subsurface ocean has been increased, while the stratification has been intensified. So the intensified stratification changed the vertical heat flux in the ocean, and in the subsurface ocean, the heat flux has been increased, but around the surface ocean, the heat flux has been dramatically decreased. So keep more heat in the ocean. And here's the profile, the temperature profile in the Weddell Sea and the Amazon Sea. We find that the subsurface temperature has been increasing both two in both two seas, and also the increased temperature may touch the continental shelf in our simulation. So that's a brief summary. So we have so many climate changes, like the surface temperature change and the subsurface ocean temperature change may both contribute to the land ice melting. That's previous work. And also previous work shows that the circulation change may contribute to the surface temperature and the ocean circulation sea ice changes. In this study, so we based on the ocean and sea ice model simulation, we find that the sea ice changes or the wind-driven sea ice changes and circulation changes may also contribute to the subsurface temperature changes and may also further contribute to land ice melting. So these zonal asymmetry changes, they could tightly link to each other. So that's the whole presentation. Thank you so much.
Thank you, Zichen. Does anybody have any questions that they'd like to type in the question box? Or yeah. Will's got a question here. Will, do you want to go and ask it?
Yeah, sure, Zichen. I was just, could you give a bit more details about your sea ice inactive experiment? So, presumably you're prescribing a climatological sort of heat and freshwater state?
Okay, thank you, Will. So what we did is that we did several sea ice inactive simulations. Basically, we fixed sea ice in the fixed sea ice concentration or extension in this experiment, but the sea ice thickness is active, based on the atmosphere ice ocean flux, and but we fixed the sea ice concentration based on the climatology in the observation, and we also fixed sea ice based on the sea ice active, the climatology in the sea ice active experiment. We find once we fix it, it doesn't matter whether it's from observation or from the model. The results are basically the same. So is that, yeah.
It does. So you say you fix the concentration, but not the thickness. So it can still change the freshwater flux due to sea ice melt and production then.
I think it's changed both freshwater and the saltwater flux. So because
Right.
you do have the bottom freezing, but you can no longer like transfer. So like the CS no longer shift. So yeah. So you can, so this process can impact on the salinity redistribution in both horizontal and the vertical direction.
I see. So it's only the motion, sea ice motion that you're turning off effectively.
Yes, yes.
Okay. Thank you, Zichin. That's great.
Thank you, Will.
We have time for another question if anyone has one. Otherwise, I've got one. The observed subsurface temperature and salinity from the Schmidt-Co paper, I think in their paper they hypothesized that the warming and the salinification were due to a shoaling of the circumpolar deep water. But your results are really interesting, and looking like the sea ice is really important. And I was wondering if you've looked at the circumpolar deep water and if you also see changes in that as well.
Yeah. So thank you, Arian. So yes. So actually, we in the simulation, in the model, so the CDW becomes warmer. So that's our simulation result. We also try to repeat Schmidt-Co's work, but maybe we don't have enough profile. So we don't have very clear result in the observation. So that's why we directly cite their paper.
Yeah. Okay, great. Thank you.
Thank you so much, Erin.
Do we have any more questions? Okay. Well, with that then, Zichin, if you could unshare your screen, please. Great. And our next speaker is Adrian McDonald. Adrian, if you could share your screen, please. Great.
Hi. Can everybody see my screen and hear me?
Yes, I can.
I can.
Okay, cool.
Great.
Okay, good. I will assume that everybody else is right. Okay, good. Good morning from New Zealand. My name's Adrian McDonald, and I work at Gateway Antarctica, which is an Antarctic research centre at Canterbury University in New Zealand. So I'm going to be talking about understanding the relationships between sea ice extent variations and surface winds at multiple temporal and spatial scales. So the underlying thing that I'm really interested in is how do winds influence sea ice? So, and I'll describe how I'm working to try and examine the influence of winds on sea ice at multiple scales. So a little outline of my presentation. So I'll be talking about how I've applied self-organizing maps to sea ice concentration data. And the aim of that was mostly to try and identify physically coherent regions based on sea ice seasonal cycle, and I'll explain why I decided to apply an algorithm to identify coherent regions based on seasonal cycle a little bit later on. I then look at those coherent regions or those classified regions and examine whether they're physically or connected to physically identifiable regions or classes. And in particular, I compare them to latent heat polynya class from the sea ice data to latent heat flux information from the Antarctic mesoscale prediction system. So basically going back to a nice simple idea of what a latent heat polynya around, can I use the sea ice data to identify these regions around the whole of the Antarctic, though I'll focus my kind of partial validation on the Ross Sea region. I then examine the relationships between the sea ice concentrations and wind speeds for the various classes. Right, okay, so I'll go on, and this is a kind of really old paper now from Holland and Kwok from 2012, but it shows the relationships between sea ice drift and winds, and also the correspondence. So that's the left panel, and the right panel are the corresponding relationships between sea ice drift and sea ice trends, so concentrations. So if you put those two things together and do some math in your head, you effectively identify that there's a positive relationship in the highest correlation region, so that increased winds cause increased sea ice at this very large scale. I did one of my PhD students a few years ago did some work where rather than looking at the large scale, we looked at sea ice area variations in the vicinity of the Ross Sea polynya. And the two diagrams here show, so effectively this student picked a small region on the edge of the front of the Ross ice shelf and calculated the average sea ice area in that region. The top diagram is the multi-year average between 1990 and 2013, and the lower diagram is the pattern for 2013. And so looking at that, we've got a nice seasonal structure associated with the polynya, and it occurred to me that lots of people have thought about the seasonality of sea ice before, and that maybe that was a good way to classify different regions and also potentially test models to decide if they've got the right seasonality in the right regions at the right time, then maybe that's a good way to work out the underlying physical mechanisms. So I will put my marker here and identify these periods during the winter period where the sea ice is high and then it suddenly drops very quickly. And so these are events where wind is blowing out sea ice significantly from the polynya region. So we did some calculations. Oh, sorry. We did some calculations basically showing the cross-correlation function. So the correlation coefficient between the magnitude of the wind vectors squared in the vicinity of the Ross Sea polynya and also the sea ice concentrations in that same region where we'd manually identified the polynya region. And what we can see is a clear negative correlation in this region. So there's a negative correlation. So if the winds are high, then you've blown out the ice out of the polynya region and the sea ice concentrations or the sea ice areas low. Though obviously you've got a response time to the winds, and you see some things. You also note that if we look at this side relative to this side, there's an asymmetry in the form of the correlations, and that's likely associated, or we identified that this was likely associated with rapid advection having an effect early on at this point, and then more gradual freezing processes occurring and closing up the polynya later on. So we've got a world where at some scales we have positive correlations between sea ice and concentrations and winds, and other regions at smaller scales where there's a negative correlation. So this is just a little movie of the sea ice concentrations variations in the Ross Sea region. A lot of the variations are rather rapid, and that probably precludes oceanic motion for some of the higher frequency stuff, and also likely some thermodynamic processes. So atmospheric forcing's important, and I'll highlight this little region here, where the Ross Sea polynya is, and also the Terra Nova Bay polynya. And you can see quite rapid changes and some bursts of sea ice being changed. Right, so I'll go on to what I've actually done. So I used the NSIDC Bootstrap version 3.1 sea ice concentration dataset over the entire Antarctic from 1979 to 2018. For each year, I calculated a seasonal cycle for a particular grid point. And then I put all of those grid points and all of those seasonal cycles for all of those years and all of those grid points into a self-organizing map. And when I form that map, I get this kind of pattern. I can tell, or a self-organizing map is a kind of clustering scheme that identifies representative characteristic patterns, but also orders them. So we can see a nice clear order here where we have low sea ices to higher sea ices and more seasonal variability here to lower seasonal variability on the bottom row. So that looks like my self-organizing map's doing something sensible. I will identify that this will be the end of season marginal ice zone, and this will be multi-year sea ice, perhaps even fast ice. If I look at the geographical structure of these different patterns, so going back to these patterns and work out where the particular positions are where this seasonal pattern occurs, I can do that for a particular year, and I can get these structures. And I can find the marginal ice zone at the end of the season or at the peak of the season and multi-year sea ice. And so the ordering makes some kind of sense. But I wanted to look at more complicated spaces like this one and try and work out if there's something interesting there. So as an attempt to validate that idea, is that particular sea ice concentration data some class or regime connecting to something physically meaningful? I've looked at latent heat fluxes from the Antarctic mesoscale prediction system from 2014 through 2016. So the leftmost panel is the lower quartile, the median, and then the upper quartile is the most right. And we can see a nice clear structure around Terra Nova Bay, the Ross Sea polynya, and a little bit about Cape Adare and this region here. If I look at my class, so this is the Ross Sea polynya pattern, or based on latent heat flux information. So what I've done here is I've effectively found the occurrence of latent heat fluxes from the ocean to the atmosphere greater than 75 watts per meter squared and plotted the density plot. So again, we're highlighting this region around the Ross Sea polynya, the Terra Nova Bay, and this corresponding diagram here is for 2014. So this is a 2014 to 2016 average showing regions where the NSIDC data is classified as polynya or a latent heat polynya. So my classification scheme works for a short period. I can apply that classification to say this is a polynya region across the whole of the Antarctic and also for every year. So I'll move on to that. So I apologize for this diagram. Thank you. But largely you can see that we see variations in the polynya size from year to year. I must admit I don't like 1988 and I'm not quite sure what's happening there, but it is a classification algorithm. But you can see that I've effectively got something that with this relatively simple analysis, which is only really taking into account the seasonal cycle, I can, from that 40 years worth of data and putting it through a self-organizing map, be able to derive the area of the latent heat polynya in this region for 40 years and do it across the whole of the Antarctic. My plan will be to, in future, will be to compare this area or these regions that are classified as latent heat polynya against the strength and persistence of winds in the region. And we can also examine the response of the polynya regions around the entire Antarctic. So I've done that very quickly here. So this is a particular, I'll just move that forwards because I've got only a few minutes left. So this, so we have the different classes. This is the polynya class. This is the correlation between the wind speed or the local wind speed and the sea ice concentration in the 3 different regions. So this first region, this one here and this one here, relate to positive relationships between wind speed and sea ice concentrations in the marginal ice zone. In that polynya class, which I've showed you, relates to areas where the latent heat flux is strong. We get negative relationships, which fits with my previous intuition. And in multi-year sea ice, we get low correlations. So they're more around the 0 line, suggesting that there's little sensitivity in multi-year sea ice regions to the winds, which is kind of what you'd expect. So it looks like it's doing an okay job. I will move to my conclusions, and perhaps I'll let you read those, and that will allow time for any questions if there are any. Thank you very much.
Great, thank you, Adrian. Does anybody have any questions? Okay, so far no questions. Adrian, could you go back one slide to your, yeah, this one. It's a really interesting result. So you've got your top left is your marginal ice zone.
Well,
is that
yes, it's at the end of the season.
Yeah. And I'm just looking at your histograms to see how many of them have the sort of positive correlations, and they're all the marginal type plots. Is that fairly, would that be a fairly broad but okay comment?
I think it is, and it's noticeable that the most negative region is the polynya region, which is where winds are acting to blow the sea ice out, which makes some physical sense. And given the fact that I've not put very much information into, well, I've put lots and lots of information into it, but the self-organizing map has found this structure without very much pushing is, I think, a nice little result, and allows me to classify the polynya around the whole Antarctic quickly and look at the relationships. So I'm relatively happy.
Yeah, thank you.
Okay, thank you.
Do you have any more questions, anyone? Okay, thank you very much, Adrian.
Thank you. I'll stop sharing.
Thank you. Okay, our next speaker today is Ed Doddridge. Ed, do you want to share your screen?
Yeah, absolutely. Can you see that?
We can see that and hear you, so thank you very much.
Wonderful. All right, well, thank you all for tuning in today. So I'm going to zoom out a little bit from the sort of perspective that Adrian was talking about and present some work that I started when I was based in the US and have been continuing now that I'm based in Australia. And I'm looking at the relationship between summertime winds and seasonal heat storage in the Southern Ocean, and then trying to extrapolate this into what the impact could be on the sea ice field. So this is work in collaboration with a number of people: John Marshall, Hajun Song, Jean-Michel Campin, and Maxwell Kelly at NASA. So let's jump into it. Now, I'm sure you're all on top of this, but I find it really helpful to start thinking about the mean state before we think about how these changes are happening. And so this is just a plot of the climatological zonal wind in the Southern Ocean. So as you'd expect, it's very windy. So we have strong zonal winds, and these two black contours represent the summertime and wintertime sea ice edges defined by the 15% concentration contour from satellite retrievals. And then if we look at the main mode of variability for these winds, which is the southern annular mode, you'll see that we end up with a strengthening of these westerly winds in that seasonal ice zone. So this, if we wanted to think about how we could affect the seasonal ice, the growth of ice, the changes in the southern annular mode winds seem like a great candidate because they're blowing in this region where we're growing and melting sea ice every year. And we also know that there's been a large trend in the southern annular mode over the last few decades. So going back to the 1950s and 60s, it was predominantly negative. And then for the last 20 years, it's been predominantly positive. And this index plotted here is the summertime one, so December, January, February, and that's shown the largest trend related to the ozone hole perturbations. As we go forward through the greenhouse gas forcings, we expect this positive trend to spread throughout the year. So we're sort of in this interesting phase at the moment where we have a predominantly summertime perturbation to the southern annular mode. And so it's important to understand what this could be doing to the sea ice at the moment. So I want to walk you through a new mechanism that my co-authors and I came up with. And so we're starting with this idea that in the summertime, we have an enhanced wind stress. So summertime SAM is a bit more positive, so we have stronger zonal winds in that seasonal ice zone. And when we blow that wind a bit more strongly, we expect to get anomalous mixing at the base of the mixed layer. Now in the summertime, we have this thermally stratified layer of water sitting on top of the cold remnants of the previous wintertime's mixed layer. So as we mix at the base of that summertime mixed layer, we're actually pushing heat from the surface down into the subsurface and mixing that cold water at depth up into the surface. So these colors here represent the temperature anomaly, not the background mean state. So in the mean, it's warmer at the surface, colder with depth, but the anomalies that we get through this enhanced mixing are cold at the surface and warm at depth. Now, after we've applied this summertime perturbation to the winds, that cold at the surface is going to draw in enhanced heat fluxes from the atmosphere. So because the SST is anomalously cold, it's out of equilibrium with the atmosphere. So it draws heat down from the atmosphere, which warms up the ocean and hence decreases this anomalous cold. But the subsurface warmth doesn't feel the atmosphere there. So what we've done now is we've increased the vertical integrated ocean heat content in the surface ocean. So we've got a positive warmth at depth, and then we've essentially damped out this cold at the surface due to the atmospheric heat fluxes. And now, as we progress through to winter, and the mixed layer deepens, which is this black line, we bring all of that warmth from the subsurface back up to the surface. So this means over a seasonal timescale, we expect the wind to create anomalously cold SSTs, which are then partially damped by the atmosphere. And then in the wintertime, anomalously warm SSTs as we bring that subsurface heat back up to the surface ocean. So if we think about what we might expect this to do to the seasonal cycle of sea ice, as we leave the summer and come through to the autumn, we have these anomalously cold SSTs. So we might expect sea ice to grow a little faster. But then as this heat comes back up to the surface, we'd expect it either to melt ice or at the very least to retard the growth of ice. So we should have positive sea ice area and extent anomalies through summer and autumn, and then a negative anomaly by the time that we get to winter. So this is our idea, and it sounds quite neat like this, but I imagine you're all thinking something along the lines of, sure, but does it really happen? So we wanted to test it. And this is a zonal mean from a gridded Argo product. It's the extension of the Remick and Gilson Argo product. And what we've done here is we've correlated the February temperature profiles with the summertime SAM. So December, January, February SAM, February temperatures from the ocean. And what you can see here is that south of about 50 degrees south, we have cooling at the surface. So that's the region where we have these enhanced westerlies associated with the positive phase of the SAM. And then this is the mixed layer, this black contour here. And below that, we have warming. Now the gray lines represent the climatological temperature. And so you can see that it's warmer at the surface. And then as it goes down, we get into the remnants of that wintertime mixed layer. So it's a bit colder. This red patch over here is underneath the region where the westerly winds have weakened because we've had that jet shift to the south. So I think that's very interesting, but I'm not going to be focusing on it today. Today I'm talking about what's happening south of 50 degrees, where we have this cooling and then warming dipole. Now there are a number of mechanisms that have been proposed to try and explain this cool SST anomaly underneath an increase in the westerly winds. And so to try and disentangle the causal mechanism here, I'm going to calculate the ocean heat content anomaly in this mixed layer region and also in this region below. And if those two are equal and opposite, then we might consider that to be evidence for a vertical mixing mechanism where we've redistributed the heat in the ocean vertically. So we've pushed some heat down and we've pulled some cold up. So if those two have equivalent magnitudes, then it makes sense that this could be a vertical mixing mechanism. If, however, we find that the cooling at the surface is substantially larger than the warming at depth, then we need some other process that's contributed to that cooling at the surface. So if we calculate these heat content anomalies, we end up with this. So the orange line here is the warming in the subsurface, and the blue is the cooling in the mixed layer. And then this gray line here that bounces around zero is the sum of those two. So this suggests, at least within the error bounds of these observational products, it looks like it could be a vertically redistributive process, which means that our idea of enhanced vertical mixing, pushing heat down into the subsurface ocean, is consistent with the observations. Now, the error bars are fairly large, so we certainly can't rule out any sort of advective contribution to it, but this is at least consistent with what I'm presenting. And then if we go one step further and we think about what's happening with the sea ice, what we have here is a regression between the sea ice extent, which is the vertical axis, and time on the horizontal axis. And so this is the impact on sea ice extent that you would expect from a +1 SAM event in the summertime. So December, January, February, the SAM is positive, and what we see is a bump in sea ice extent through March, April, May. So that's the autumn time. And then we come into winter, June, July, August, and that sea ice extent anomaly goes back to zero. And then as we get to September, which is the sea ice maximum, it's negative and it stays negative for the rest of that year. Now these negative values are not statistically significant. So while I would like to say that this is exactly what we predicted, there is some uncertainty within these observations. And so this could very well just be nothing. But this signal here, the positive signal through March, April, May, is statistically discernible from zero. So we do see a bump in the sea ice extent related to these summertime winds in the autumn. Now, because the observations are
5 minutes to go it.
Thanks, Irene, are somewhat limited, we turn to the model world to try and explore the mechanism in a little more detail. So what we have here is a very idealized channel model that has temperature, salinity, sea ice, but a repeating annual cycle of 4 things at the surface that we can change and put in a positive SAM. So that's exactly what we did. We increased the strength of the zonal winds as if it were a positive SAM. And then we saw a pattern very similar to what we found in the observations. Cooling in the mixed layer warming just below the zonal mean mixed layer depth. But because this is model world, we can now diagnose a heat budget. So if we look in the blue box and the red box, we can work out exactly what mechanisms are causing that cooling and the warming. And so over here, you can see that in the mixed layer, vertical diffusion is almost solely responsible for the cooling. We have a small contribution from horizontal advection and vertical advection, but the bulk of the work is the diffusion. Below the mixed layer, it's the same story. We have vertical diffusion causing that warming, and vertical advection is a slight cooling. So that's Ekman upwelling of the cold water from below, but it's overwhelmed by this diffusion. Now, the other impact that we would expect from this enhanced diffusion is a deepening of the mixed layer. And that's exactly what we see in the model as well. So this is the control mixed layer depth and the perturbation ensemble mixed layer depth. And they're different. The perturbation is deeper, just as we would expect. We also tried something very similar in a global coupled model, where we imposed an ozone hole to give us a positive sand perturbation. And we found in sea ice area, which is the blue curve, that we got a positive response and then it comes back towards 0. But when we looked at sea ice volume, we did have this negative anomaly, which was then discernible from 0. So this suggests that sea ice volume is perhaps more sensitive than sea ice area, which means that even if we're not changing the area covered by sea ice, we're reducing its thickness, which makes a lot of physical sense. As we have more of this warm water that comes up towards the surface, it reduces the volume of the ice that we can grow. Unfortunately, in the absence of a long-term, large-scale sea ice volume data set, this is very hard to access observationally, but it's a tantalizing result. So just to wrap up here, I've shown you this novel mechanism that we developed thinking about how the summertime winds could affect the seasonal cycle of sea ice and the surface ocean over the next year. Showed you some evidence from observations that was at least plausible, and then dived into the model world where we found very strong evidence to support this idea of enhanced vertical mixing and some suggestions that sea ice volume might be more sensitive to these summertime winds than sea ice area. So thank you very much for your attention.
Thanks, Ed. Does anybody have any questions for Ed? Okay, I'll start with one. Ed, the results you're presenting, are they for zonally average sea ice area?
They are, yes. These are all hemispheric scale results at the moment.
And have you looked into regional variations? So regions further north might be more affected by the SAM, whereas regions closer to the continent might be more affected by the coastal easterlies.
Yeah, we haven't yet, but I think that's a really exciting avenue to take this in the future and to think about how smaller scale wind indices might be more relevant for these regional results as well.
Yeah. Thank you. And we've got another question. Hughes, do you want to read your question out?
Yes, so thank you very much for the nice talk. So you mentioned that a larger heat uptake in autumn, but you could also have a larger heat uptake in summer if the ocean is colder. How does it fit with your mechanism if you have a larger heat uptake in summer too?
Yeah, that's a really good point. So over here on the left on the schematic, it actually wouldn't matter hugely when that heat uptake is happening. It's just easier to put the arrow over the autumn in the schematic. But we would expect as soon as that SST is anomalously cold, then it should induce an anomalous heat uptake.
Okay, do we have any more questions?
Narrowly raised her hand.
Okay, go ahead.
Hi, thanks Ed for a great talk. I was wondering where you showed the profile of the perturbation of the mixed layer depth, it seemed to have sort of like a double peak in it. Is there something to that, or is that just sort of within the sort of the noise?
Yeah, that's just a quirk of the surface forcing that we were using that had a bit of a double jet during the summertime in this particular spot. So I don't think that has larger significance.
Okay, thanks.
Okay, and Will's got one more question. Go ahead, Will.
It was really just a response to Hugues' question, in the sense that a summer SST anomaly, I wonder how much that just reflects changes in sea ice cover, in which case you start getting complicated issues like albedo feedbacks. It was really just a comment and a question, I guess.
Yeah, I think that's a really good point, Will. If we're looking further out in the marginal sea ice zone, then we wouldn't expect that to be too much of an issue. But when we're close up against the summertime sea ice edge, then absolutely, changing the SST is intrinsically related to the local sea ice coverage.
Yeah, okay, thanks, Ed.
Great. Okay, thank you, Ed. We'll now move to our last speaker, Holly Ayres. Holly, would you like to share your screen?
There we are, just had a moment there. Yep, just one moment. Here we are. Can you all see that okay?
Yep, that looks great. Thank you.
Thanks. Yeah, hello and good evening from the UK. Thank you for all the conveners for putting this together. I'm a PhD student at the University of Exeter working with James Green, and I'm going to talk a little bit about my project on the coupled climate response to abrupt Antarctic sea ice loss. So using the coupled HAD-GEM3 GC 3.1 pre-industrial control model, which is the Met Office low resolution N96 1-degree model, we induced an albedo feedback mechanism where we basically set all of the Southern Hemisphere sea ice to a melt bond. So this was run for 300 years, and it triggered an instant abrupt decrease in sea ice within the first 5 to 10 years, with a spin-up period of about 20 years. So everything I show from here is the statistically significant response when compared to the pre-industrial control. So here we have the seasonal spatial plots of sea ice concentration and turbulent heat flux from the ocean to the atmosphere. The first thing to note is the significant ice loss and the exchange of heat between the ocean and the atmospheric boundary in the Southern Ocean. The second thing, where your eyes may be averted to, is we get this response in the Arctic, albeit a much smaller magnitude, a response nonetheless. Now, just to be clear, this is a response to Antarctic sea ice loss, so it's not its own thing. So this triggered some new questions, basically on cross-hemispheric dynamics, which we're basically currently still exploring. We've got a paper in preparation. Not everything is completely finished, so hopefully I'll be able to explain everything as well as we can at the moment. So again, here we have some seasonal plots, the first order response. I'm aware that there's a lot of information, so I will just focus on a few key results. So everything in the Southern Hemisphere is more or less what we expected. So the limited studies on the response to Antarctic sea ice loss do show similar results. Warming over sea ice loss regions, increased sea level pressure over the continent, a weakening of the tropospheric eddy-driven jet, a slight increase of precipitation over the Southern Ocean. One thing to note with the eddy-driven jet, I haven't included it here, but there is a there's no real shift or anything like that, no equatorward shift, as we might expect. So yeah, this is the opposite to what we would expect in the increased CO2 scenarios. In the tropics and into the Northern Hemisphere, we see this kind of mini global warming response. And by this, I mean with a warming, specific features like a deepening of the Aleutian low in the North Pacific, which hints at possible wave train mechanisms, corresponding winds, and this interesting southern shift in the ITCZ. So this has led us to hypothesize that there are two main mechanisms at play. The first being directly related to sea ice loss in the Southern Hemisphere. So this is kind of like a fast response, inducing a localized warming effect. And then this reaches the tropics through an ocean atmosphere teleconnection, maybe driven by SSTs, El Nino, ENSO, that kind of thing. The response is then propagated to the northern hemisphere. So, for example, as I've already mentioned, the Aleutian low. And this enhances the southern hemisphere response as well. So, for example, we have the, in the South Pacific, we have an increase in the ASL, the emergency low. MSA possibly related to ENSO, but still needs to do a bit of analysis on this to get the exact mechanisms there. So yeah, this happens through tropical teleconnections in both hemispheres, and this is kind of like our slow response. So I won't focus on this slide too much, but I just wanted to point out the typical upper tropospheric tropical global warming fingerprint to point out this global warming response induced by Antarctic sea ice in the zonal mean temperature anomalies, and this dynamic response directly to Antarctic sea ice loss in the southern hemisphere. Clearly, there's a lot going on in the northern hemisphere as well. But breaking down exactly what that's responding to, whether it's the warming in the tropics or respective Arctic loss, when it comes to the things like dynamics, is a little bit tricky, but again, something we are currently working on. So just to look at some really basic time series of sea ice area, we wanted to assess the response and when it gets to the Arctic and triggers the ice loss there. And it's clearly about 30 to 40 years after we've set off this initial ice loss in the Antarctic. It's variable, there's a lot going on, there's a lot of internal variability here, but this helps us to break down the fast and slow response. So notice that also in the southern sea ice area response, there's this slight downward trend again, sort of after the initial abrupt change. Which we think is again due to this slow mini global warming style second order response. So in terms of temperature, we see this abrupt increase and the slight warming again thereafter in the southern hemisphere, not much different to what we see in the sea ice. In the tropics, there's this gradual warming over about 50 years from the first decade. And in the northern hemisphere, we find that it takes again about 30 to 40 years to get a response. Again, it's similar to the sea ice. So what is going on in the tropics? So I guess this kind of takes the focus away directly from the Southern Ocean and everything. But basically, we think it has something to do with this shift in the ITCZ and the shift in precipitation, particularly in the Pacific, which in part comes from atmospheric warming, but also ocean warming and SSTs, as we can see from this warm anomaly here. So the SST with global mean removed, we have this big warm patch in the sort of central Pacific there. So I'm still trying to understand exactly what's going on here. I'm currently working on this, more analysis, trying to pull this all together. So this is something that's also been seen in another study, Mark England's recent paper, which uses a different method, ghost flux method in the CCSM model. However, we do have a few differences and yeah, they're not all the same. So I won't focus on the ocean as I have a whole section of this. If anyone's interested in discussing it separately, then yeah, that would be great. But I just wanted to add a couple of things in to show the impact on the ocean and show that it's not just all happening at the surface with the SSTs. So here we have the annual means of temperature, salinity, and density. As you can see, the response is extensive and is again similar to that sort of mini global warming response, down to even the spatial magnitude, particularly in the temperature there. And these density changes are also really important in meridional heat transport and water mass transformation, etc. Just a quick point on the Antarctic circumpolar current. So there's actually an average of about 20% decrease in the ACC strength at Drake Passage. And it takes this deep ocean current about 50 years to properly react to the changes in the wind, but of course there may also be other influences like ocean mixing and things like that. So I just wanted to also add on a couple of slides on some recent atmospheric only simulations that we ran. So we took the sea ice from the coupled model, and we basically put it into an atmospheric only model, and we run it for 200 ensemble members, so we could get as much internal variability and all of that sorted out. So yeah, we wanted to basically work out whether ocean coupling was important in this response. And as you can already see just from the sea ice figures here, there's no Arctic response, and that's a pretty key result, and there's no real cross-hemispheric thing going on here. So yeah, I think it's quite interesting. And in terms of spatial magnitude of the response, we kind of see that from the coupled model, there's also no comparison. So temperature is confined to the Southern Ocean and does not even extend far into the continent, something that we've seen before in other studies. Again, so much smaller decrease in tropospheric eddy-driven jets, and limited precipitation changes that are confined to the Southern Ocean. So it doesn't really seem to be much going on away from the Southern Hemisphere. So this is very new work, and again, will hopefully contribute towards this paper, and we can hopefully get a real nice sort of picture of the coupled interactions there. So just as a summary, the response to abrupt Antarctic sea ice loss can be split into fast and slow. The fast response is like the dynamic changes to the local climate. So the things that are opposite to the greenhouse gas forcing, for example, the eddy-driven jet, subannular mode, that kind of thing. The slow response is this mini global warming through teleconnections with the tropics. From the tropics, the global warming response is enhanced in the Southern Hemisphere, and it's propagated to the Northern Hemisphere, causing an Arctic sea ice loss. So the coupled ocean, as I've mentioned, is crucial, as we've seen from these atmospheric only simulations as well. So yeah, that's everything. Thank you everyone for listening.
Thank you, Holly. Do we have any questions? Okay, I'll have one question. So your response in the tropics,
yes,
is that, could you go through the mechanism of how the tropics is responding to the Antarctic ice loss again?
Yeah, so that's a good question. So this is something that still trying to, we still need to do a little bit more analysis to sort of solidify this hypothesis. But the idea is generally that we have this kind of SST warming that is getting to the tropics from the southern, sort of the Antarctic sea ice loss. And then this kind of, I guess, possibly through ENSO, again, a lot of work needs to be done here, is basically propagating. So for example, to the Northern Hemisphere, we have if I just go back to this slide here, so if we look at the MSLP, particularly in DJF and MAM, we have this deepening of the Aleutian low. This has been studied when we've looked at some teleconnections with the tropics to the Arctic, particularly McChrystal 2020 has recently looked at this. And I think that Mark's also looking at this as well. But yeah, so basically there's a potential wave train mechanism that brings the heat and the interactions to the Arctic. For the Southern Hemisphere interactions, we're thinking it's potentially through ENSO. I think it's El Nino that tends to weaken the ASL. I might be wrong, might be La Nina. But yeah, so that's what we think is going on here, and there's quite a clear weakening of the ASL again in the mean sea level pressure in the South Pacific.
Okay, Great, thank you. We've got 2 more questions. Rob, do you want to ask your question first, please?
Yes, thank you, Ariane. Thank you, Holly. Just a very quick question. Sorry if I missed it, but what do you mean by abrupt sea ice loss, please?
Yeah, so basically, we basically triggered this for sort of albedo feedback. So we set all of the sea ice in the Antarctic to a melt pond, which triggered this albedo feedback. And within the first 2 years, we got this huge ice loss. And so, yeah, that's kind of what I mean by abrupt there. As you can see, this happens within, well, bring this over here. So this happens within sort of the first 5 years or so, and then it starts to level out a bit there. But yeah, it's not really a realistic situation, but yeah.
Yeah, thank you, Holly.
Great, thank you.
Great, thanks. And Nerali has a question as well. Nerali, would you like to read it out?
Yeah, thanks, thanks, Holly. I was interested that in your experiments you see that by losing Antarctic sea ice, you have these series of effects, and in the end that also affects Arctic sea ice. And so I was just wondering if the reverse is also true, and does Arctic sea ice loss potentially affect Antarctic sea ice, and sort of what sort of timescale is that response likely to show up on?
Yeah, that's a really great question. Short answer is, I guess I don't know. I know that there have been a few studies that have started to look at this, DESA SL, and a couple of others, I can't remember off the top of my head, that look a little bit at this Arctic cross-hemisphere response. But my educated guess would be that there's a lot more sea ice loss in the Arctic. So I think that it would be possible, but I guess it also depends on the land side of things and the connections that the southern hemisphere has with ENSO and through the Pacific. So yeah.
Okay, thank you.
Okay, do we have any more questions? I don't think so. Thank you, Holly, and thank you to all of our speakers from this session. We've now got time for another break, and we'll reconvene in about 11 minutes on, am I reading that correctly? On the hour, yes. So see you all soon.
How do I turn off screen sharing? No.
Because focusing on the ocean. It really is a beautiful day here in Hobart. It's too bad you guys can't be here, but thank you for dialing in anyway. Our first speaker is Andrew Stewart from UCLA. Andrew, are you ready to start speaking?
I am.
All right. Well, I think if we're ready to go, then we'll take it away. Just as with previous sessions, I'll give you a 5-minute warning and then try and wrap things up. Okay. Andrew Stewart.
Great, thanks, Will. I'd like to start by introducing myself. I'm Andrew Stewart. I'm an associate professor at UCLA. And thank you to the session organizers for pushing on and organizing this oral session online. I think it's been a great idea and it's been very interesting so far. This work is actually drawn from a couple of different studies, and so there's various different authors involved. I'd particularly like to acknowledge Clara So, my graduate student who is really responsible for driving the work forward now. This talk concerns the controls on transport of ocean and sea ice in the Antarctic slope current. I expect most of you are familiar in some level with the Antarctic slope current. In this figure here, we illustrate the circulation of the Antarctic slope current via the sea surface elevation in the bottom right panel here. Antarctic slope current essentially follows the Antarctic continental slope almost all the way around the Antarctic continent. It's also visible in sea ice drift. This is winter zonal sea ice drift from feature tracking algorithms. And you can see again, almost all the way around the Antarctic continental slope, highlighted by the dashed black line here, there is a westward flow of the sea ice, particularly concentrated close to the coast. Now, the Antarctic slope current is important for a number of reasons. One is that it modulates the exchanges between the open ocean and the Antarctic continental shelf. It's also also responsible for the redistribution of sea ice and ocean properties around Antarctica. Yet surprisingly, there is relatively little fundamental understanding about what sets these transports. Now, one obvious driver is the wind. It's been brought up in this session already. In the top left panel, we show the winter averaged zonal winds around Antarctica, and the westward drift of those winds close to the continent actually has a great deal to do with the westward flow in both the ocean and the sea ice. But the short version of this talk is that actually the interaction, mechanical interaction between ocean and sea ice and atmosphere in the Antarctic slope current is much more complicated than one might expect, with other drivers also being actually quite important in setting both the sea ice and ocean transports. One of those, for example, is the ocean tides, which we'll come back to later in the talk. So what does drive the flow of sea ice and ocean in the Antarctic slope current? I'm going to pose here a naive expectation, something of a specialty of mine. And that expectation is that as the winds blow to the west over the Antarctic slope current, this is illustrated up here, they transfer momentum into the sea ice field by frictional stresses, probably not too controversial. And then that momentum is transferred further down into the ocean by the establishment of a shear between the sea ice and ocean flows, again, both to the west, here pointing into the page. Then that momentum is further transferred down through the ocean into the solid earth via form stresses or frictional stresses against the sea floor, and thus you have a balance of momentum. Ultimately, momentum sourced from the winds is removed via transfer to the solid earth. Now, it's going to turn out that the actual picture is potentially different from this, and at present, we really don't have a firm understanding of this process for the usual kinds of reasons, the paucity of measurements around Antarctica, and the high resolution required for ocean sea ice models to faithfully reproduce the dynamics in this region. So the first thing I'm going to show you is some results from a very high resolution global ocean and sea ice model. This model, the LLC 4320, was run at NASA at a global resolution of 1/48 degree for 1 year. I'm not going to say too much about it, except for, it has various caveats, including a short duration and the enormous amount of model output, which ranges in the several petabytes. So if you were thinking of running your favorite analysis on this model, then you might want to think again. I'll highlight some more caveats to this model in the next few slides. But we actually published an entire paper on the dynamics of the Antarctic slope current in this model already last year, and I just want to highlight some key findings from that study. So one finding is illustrated in the following sequence of images. I'm going to show you the flow in the sea ice and subsequently the ocean in a sector of the Antarctic coastline around East Antarctica. So this is longitude on the x-axis here. Here we're showing the time mean averaged over an entire year, sea ice zonal velocity. And what you can see is that these colors in blue correspond to westward drift of the sea ice. And so there is generally, as we'd expect, a westward drift of sea ice all through this Antarctic slope current region. The black contours here correspond to isobaths, i.e. contours of constant ocean depth. And you can see that the sea ice flow is actually has a peak over the continental slope. There seems to be a jet. This is already perhaps surprising because the wind has no such jet, and the sea ice and ocean somehow seems to have self-organized into a jet along the continental slope. Perhaps also surprising is that the ocean also has a jet along the continental slope. The ocean flow has a strong maximum also over the continental slope, exactly under the sea ice jet. And in fact, it turns out that the strength of those jets almost exactly match one another. This is true almost all the way around Antarctica, and it's true on an annual mean, with some fluctuation season to season. And the result is that there is essentially zero ice-ocean shear all the way around the Antarctic slope current. And as a result, there is no stress felt between the sea ice and the ocean. As the sea ice flows, exactly where the sea ice flows fastest, it feels no frictional stress against the ocean because they go exactly the same speed. This is illustrated by this figure in the bottom, where essentially think of this as an average along the current. And we're showing in the purple and turquoise curves the average speed of the ocean and sea ice, and just shoreward of the shelf break, which is around about this location here, we find that the ocean and sea ice speeds match, as you have taken from the previous figures. And as a result, the ocean ice stress, which is the pink curve here, vanishes. So the ocean over the continental slope, the ice feels no stress. The ice ocean stress goes to 0. So this is a very puzzling phenomenon, but the gist of it is that this picture is very different from the naive expectation I posed earlier, clearly, and the momentum transfer from the ice to the ocean goes away in the core of the slope current. Now, another caveat of this model is that it doesn't offer enough diagnostics of the sea ice to allow us to really interrogate what's going on in the sea ice dynamics. So my student, Clara Sir, has set up this idealized process-oriented model to try and really isolate exactly what's going on in this sea ice ocean Antarctic slope current system. I don't want to go and spend too much details spend too much time on the details of this process-oriented model. The gist of it is it's an high-resolution ocean sea ice simulation in a reentrant channel with a fixed atmospheric state that is spatially uniform except for the winds, whose profiles are shown up here. The sea ice state is largely prescribed by an inflow from the southern boundary. So essentially, the dynamics are largely governed by the mechanical interaction of the sea ice and the ocean. So what do we find in this model? Well, I claim that this model qualitatively reproduces the same findings that I just showed you from that global high resolution model. In these panels here, I'm showing you the flow of the ocean and the sea ice averaged over several years in this model. The ocean state on the lower panel here shows you the ocean velocity as a function of latitude and depth. Here, negative values correspond to westward flow. So again, westward drift in the ocean everywhere, which is what you'd expect of the Antarctic slope current, with a maximum over the slope, also what you'd expect of a slope current. But more pertinently, the upper panel shows the mean speed of the ocean and at the surface and the sea ice, which again almost perfectly match over the continental slope. And what the advantage of this model is that it allows us to dig in and actually interrogate the model and understand really what's going on here. Why do we see this matching of the sea ice and ocean velocities over the continental slope, this strange configuration of the momentum transfers? And what's happening, I'll draw your attention to this lower right panel down here. It turns out this is the momentum balance in the sea ice. And here, again, negative values correspond to westward accelerations. So the wind stress is accelerating the flow of the sea ice everywhere to the west. And it turns out that over the continental slope is actually balanced by sea ice internal stress divergences. So actually what's happening is sea ice internal stresses are sucking up all the momentum that's coming in from the wind and then dumping it somewhere else. And you can actually see that it's dumping it largely onto the continental shelf. In the ocean, as a result, the ocean feels no surface stress from the sea ice. The ice-ocean stress, this brown line here, is basically 0 over the continental slope. And the only accelerations of the ocean that are left are, in fact, accelerations due to tides. This process called tidal rectification I won't get into right now. So it's really this really gives us some more insight into what's going on. Schematically, what's happening instead of that naive expectation I posed earlier is that momentum does indeed come into the ocean, into the sea ice from the winds. But instead of being transferred to the ocean ends up accelerating to the same speed as the sea ice. And so instead of the momentum going downward into the ocean via ice-ocean friction, you now instead have the sea ice developing shears between this core of the slope current and adjacent regions, and internal stresses in the sea ice transferring momentum out of the slope current, where it can then be transferred into the ocean. 5 minutes. Transferred to the sea or elsewhere. Thank you, Will. So this is a fundamentally different configuration of the momentum balance from at least my naive expectation. And I'm not going to get into the explanation in too much detail, but the reason why the ocean accelerates to the same speed as the sea ice is that the mechanisms of downward momentum transfer in the ocean are made very inefficient by the steep continental slope. And as a result, the ocean can sustain large along slope velocities without losing any momentum at the seafloor. and consequently it can just freely accelerate to the same speed as the sea ice, and thus the sea ice and the momentum balance ends up being balanced instead by these lateral transfers of momentum. So what are the implications of this configuration of the Antarctic slope current in the sea ice and ocean? Well, to illustrate that, I'm showing you the results of a series of perturbation experiments that Clara has performed by independently varying various parameters in her model. As you might expect, the sea ice transport, which is shown as a function of each of these parameters, is strongly sensitive to the atmospheric winds. But it's also, more surprisingly, very sensitive to things like, say, the ice thickness. The ice thickness changes the efficiency of horizontal momentum transfers by internal stresses because it affects the rheological formulation of the sea ice model. And so as a result, in this case, we find that increasing the ice thickness actually decreases the speed of the sea ice. That's perhaps not that surprising, but the explanation at least is clear based on the mechanism I just articulated. But furthermore, also processes that accelerate the ocean are important for determining the sea ice transport. For example, the strength of the tides have an impact on the sea ice transport. And the horizontal buoyancy gradients, which are shown here, the horizontal salinity gradient, in fact, across the Antarctic slope current, implying that buoyancy forcing across the slope current should also be influential on the sea ice transport. And of course, all of this goes the other way. Because the sea ice and ocean speeds basically match in the slope current, anything that changes the sea ice speed must essentially always change the speed of the ocean and thus the ocean transport as well. So I'm going to summarize with a few key takeaways here. Essentially, we're finding that the momentum balance of the Antarctic slope current is strongly influenced by sea ice internal stresses, which redistribute momentum input from the winds horizontally, where they must be removed from the ocean sea ice system elsewhere. The implication is that the ocean and sea ice transports in the slope current are very tightly coupled, and that both become very sensitive to things like the ice rheology, to the winds, obviously, but also to things like the tidal and buoyancy forcing in the ocean. We're now taking this work forward by using it to look at the sensitivity of the cross-slope transport in the ocean to the sea ice as well. So the overturning circulation and the transport of heat toward the Antarctic continent. So with that, I'll conclude and thank you for your attention.
Great, that's great. Thank you, Andrew. I have a number of questions, but we've only got a certain amount of time, so other people better get in quick. Rob Massam, can you, and maybe Rob first?
Hi, Andrew. Thank you very much. Sorry again if I missed it, but have you investigated the effect of the meridional components of the winds and the currents, please?
Yes, I just didn't mention it because the results turned out to not be very interesting. So that's actually this panel over here is the meridional winds, and there is a very modest sensitivity to the meridional winds. But you know, we co-vary the inflow of sea ice at the southern boundary with the meridional winds to make it self-consistent, but we don't find a strong sensitivity there. I guess it's not immediately obvious to me why I'd expect a strong sensitivity. But I'm open to alternative arguments if you have one.
Oh, no argument, Andrew. Just wondering about maybe the localized effect of katabatic winds, etc. So that
Right.
was me. Thank you.
So in a more realistic geometry with, for example, localized coastal lineas, etc., then the picture is going to change a lot. We really just isolated the slope current here, and that pertains to Ed's question as well. If you had sorry, Ed, to steal your question. If you had a jagged coastline, a more realistic varied coastline, how would that influence? Hard to say. All I can say is that in the isolated process-oriented model and in the high resolution, comprehensive model, we seem to see the same thing. So we think that the process-oriented model is capturing the essence here, even though it's missing out some of those important coastal processes.
That's fantastic. Thank you, Andrew, for some very quick answers there. So we'll move on to our next speaker. If Andrew, you can unshare and swap with Steffi Libera, who is talking about the ocean's role in driving Antarctic sea ice variability.
Thank you, Will. So I'll try to share my screen.
Okay, Steffi, we're ready whenever you are. Yep.
Yep, thank you. So hi everyone, I'm Steffi and I'm a PhD student from the University of Tasmania. And I'll be presenting my research on ocean's role in driving Antarctic sea ice variabilities. So for my project, the interest is in understanding the ocean and sea ice interactions in the Southern Ocean. And for that, we are using predictability as a tool to look at how the ocean influences the Antarctic sea ice variability. And in this analysis, we'll be using both observation, that is satellite sea ice data, and also model outputs. So the focus is on predictability. And the previous studies have already identified that the ocean can sustain heat anomalies and then influence the sea ice from one season to the other. And they've recognized two main modes of predictability, that is persistence and reemergence. So, and it's been connected to how the surface ocean and the sea ice evolves through the different seasons. So here in this schematic, I'm trying to, in a very idealized way and simplified way, show how the different seasons are different. In the different seasons, the surface ocean and the ice conditions vary. So if we start in winter, we have cold surface conditions, and then we have the ice formation. And the ice formation will further cause brine rejection and vertical mixing. That all of this will result in a deeper mixed layer formation in the winter. And in the summer season, the ice would melt, forming a freshwater layer on the surface. And then it can be further warmed due to radiative forcing. And so in the summer season, you have stronger stratification. And then in the following season, again, as the surface cools down, this stratification layer or the stratified layer will be a very simplified concept of how the ocean and ice evolves through the different seasons. And going back to the two modes of predictability, that is again represented using a simplified schematic here showing the correlation with the time lag. So if we have a persistent signal, we have a high correlation value through the first few initial lags, and then it gradually fades down. So shown here with the dotted line. And if you have a reemergence signal, you have a high correlation in the initial lags, which fades down in the intermediate lag, and then the correlation value starts to rise up again or reemerge. So these are the two signals. So now how is it connected to the ocean? So when you have a deep mixed layer, we can also think about it as a larger volume of water having similar properties. So overall, mixed layer is the homogeneous layer with the same properties as of the surface. So when you have a larger volume of water having similar property, that actually enhances its capacity to sustain the surface ocean conditions. In that case, having a deeper mixed layer actually enhances the ocean to have a persistent signal of predictability. But then when we think about reemergence, that is when the seasonal evolution of the surface ocean comes to play. So when we have the deep mixed layer in the winter, and then the summer stratification will actually disconnect the cold water underneath that stratified layer from the surface. So you won't get any predictability in that season. But then when the stratification layer or the stratification erodes away, then you get these cold anomalies that's been sustained in the ocean back to the surface, producing reemergence. So that would almost give a very simple background of the predictability of Antarctic sea ice that's produced by the ocean. So in my analysis, what we've done is at first we are using the satellite sea ice data, and then we calculate the total sea ice area and produces a monthly time series and then compute the lagged correlation. So in this figure, what I've done here is you have the lead months on the y-axis and the lag months on the x-axis. So each of these lead months have been correlated against the 12 subsequent lag months. So for example, here, January is being correlated against February, March, and so on until January of the following year. And similarly, it's been the same calculation has been conducted for each of the lead months. And then we've just shifted the cells so that we can align all the lag months together. Now, I've already mentioned the two main modes of predictability, and looking back at the two of those concepts. So when we have a persistence, we have a high correlation value that lasts for a first few lags and then slowly fades away. So here, looking at the first block in the summer season or the summer months, you start to see that the correlation values were lasting for a few months, and then that persistent pattern or that block is slowly fading down. So here in January itself, you have the strong persistence for about 6 months. And then this pattern is slowly fading down until winter, where another strong pattern of persistence is happening. Now, when we look at the spring months, we can see that in the initial lags, you have a strong persistence. And then in the intermediate lag, you don't see much persistence, or the persistence or all the correlation values have declined. And then in the subsequent lags, here you can see that the correlation value starts to pick up again or re-emerge. So this is a signal of re-emergent pattern. So, so we have an introduction to the two main modes of predictability. So we've done this analysis for all the sea ice area around Antarctica, and we've divided it into 5 sectors. So the King Haakon sector, East Antarctic sector, Ross Amundsen sector, and Amundsen-Bellingshausen sector. So when we look at the results, we see that there's variability between the different sectors. There's difference in the strength of it, the timing of when these patterns occur, and also the duration over which these predictive patterns are sustained. So once again, focusing on the same modes of predictability, the persistence and reemergence. So we've sort of marked down some of the main patterns in there. So we can see that most of the sectors show a predictive pattern in the winter months, and except for Weddell. So most of the sectors have predictive patterns in the winter months, except for Weddell. But in the Weddell sector, you have a strong persistent pattern occurring over the summer months, and something similar in the Ross Amundsen sector. Now, again, looking at the reemergence, we see that in the East Antarctic sector, there is a reemergent pattern from the summer lead months towards the spring lag months. But for Ross Amundsen, Amundsen-Bellingshausen, and the Weddell sectors, we have reemergence from the spring months towards the winter months. So that actually gives us some idea about the different sectors, varying strengths, and the different patterns. So we've conducted a similar analysis with the ocean, with the ice outputs from the model. So as I've mentioned before, the interest is to look at the ocean-ice interaction. So we're using the ocean data from the model. So we also looked at how the model outputs of the ice would represent a similar predictability. And when we compare the different sectors, we notice that most of the sectors are comparable, but the large deviation is occurring for the King Haakon and the Weddell sector. And for the model, it's still it's actually doing a really good job at still picking up the persistent and re-emergent signals. So in most of the cases, it's capable of producing the persistent signal and the re-emergent signal. And so with that actually gives us some confidence in going ahead and looking at the ocean model. So for explaining the ocean analysis, I'm actually using 2 sectors to compare. So for that, I'm using the Amundsen-Bellingshausen sector and the Weddell sector. So looking at all the results of all the 5 sectors, we can see that in the Weddell sector, the prominent mode of predictability would be re-emergent signal, whereas for the Amundsen-Bellingshausen, you do see some persistent signal and some re-emergent signal, but it's not as strong or prominent as the rest of the sectors. So here, I'm going to go with 1, 2, 3, 4. So first, again, just mentioning again the predictability.
Steffi.
Yes, thank you, Will. Predictability signals from the model. So you have the strong re-emergence pattern in the Weddell sector. And then in the Amundsen sector, you see the persistent signal. Now, these are the 4 plots here are the ocean analysis ones. And so what we have done is latitude depth sections. And we're showing the climatological mean for winter and summer. So it is temperature profile with the salinity contours, and the thick white line is the mid-layer depth from the model. So when we look at the 2 different seasons represented by the model, we can see that in both the Weddell sector, the first row is all for the Weddell sector, and the bottom row is for the Amundsen sector. So when we look at the difference between the winter and the summer for these 2 sectors, we see that in both Weddell and Amundsen, we do form deeper mid-set layer in winter, and they look similar. But a large amount of difference occur between the summer sections for these 2 sectors. So if you look here, especially if we focus on the isohalines, we see that they have been quite concentrated, or the stratification is really strong in the Weddell sector, whereas in the Amundsen sector, they are much more coarser, or the stratification is quite weak. And also when we look at this cold layer of water underneath this surface stratification, we see that there is a cold winter mid-set layer, cold and deep winter mid-set layer forming, but that erodes away in the Amundsen-Bellingshausen, but that's been really sustained in the Weddell sector. So going back to the concept of re-emergence, we needed the ocean to retain some of the property in an intermediate season, but not being expressed at the surface. So the very strong stratification here allows this layer to exist here, but not being expressed as a surface, allowing it to form a very strong re-emergence. Whereas for the Amundsen-Bellingshausen sector, although the model mid-set layer shows a shallow depth stratification, and in fact, it is showing persistence during summer. So when you don't have a strong stratification, deeper layers of the with the surface ocean property anomalies, leading to persistent signal. So that kind of sums up the ocean analysis. To summarize, we have looked at the predictability for the observation and the model, and we've seen both persistent and re-emergent modes. And we also noticed there is regional variability for the different sectors. And from the initial results, we can note that the ocean plays a role in the spatial distribution of the predictability. Thank you.
Okay, thank you, Steffi. That's great. Time is moving on, but maybe if there's one quick question while Steffi unshares and our next speaker shares, somebody could ask. But otherwise, we've got a question from Oog.
Yeah, so thank you very much. Sorry if I missed something, but it seems from your figure that you have also some re-emergence in summer, while it's more standard to have re-emergence in winter. How would you explain, if I've seen correctly, such a re-emergence in summer?
Yes, that's a very good question. That's in the East Antarctic sector. And actually for that summer season producing a re-emergence, I can't really think of a positive mechanism there. There's only certain hypotheses at the moment. So we'd still be working on that.
Okay, thanks.
Yes.
It'll be interesting to know what are the mechanisms.
Huh?
So I would be really interested to see what are the mechanisms there, because it's, yeah.
Okay, yeah.
It's very interesting.
Thank you.
All right, so we'll move on to our next speaker, Steve Ackley, who is talking about modeling new ice formation under the influence of ocean waves. Take it away, Steve.
Okay, you can hear me okay?
Yeah, it's all great. Thanks, Steve.
Thanks. Yeah, I'm going to discuss some, basically it's kind of a conceptual modeling effort that we're undertaking with some rationale because of the some recent investigations that we had. So if I can change slide here. There we go. Basically, the motivation for this is we've already known for a long time that ocean waves have an influence on ice formation in the marginal ice zones in Antarctica. But recently, we had an expedition into the autumn Ross Sea area and made some investigations under a project called Polynyas and Ice Production and its evolution in the Ross Sea. So we entered the Terra Nova Bay, Polynya particularly, and found that the ice production there seems very linked with ocean waves. We're interested in the ice production because of its effects on formation of water masses. The Polynyas are major ice factories, and so the rejection of salt leads to a lot of transitions in the salinity of the formation of high salinity shelf water, and also into the ice production in the sea ice extent in the Ross Sea. So the Piper's measurements in the Terra Nova Bay showed that we had swift buoy measurements of high wave fields whenever katabatic winds are present. Extreme sensible and latent heat fluxes and katabatic wind events were also influenced by waves. And new ice formation is dominated by wave-generated pancake ice in the Terra Nova Bay area. And as I mentioned, there's also an interest in pancake ice formation in the Arctic and Antarctic marginal ice zones during ice advance, which I'll allude to at the end of the talk. So this is a SAR image of the Terra Nova Bay area. This is the Weddell ice tongue. There, the coast of Antarctica is on the side here, the Victoria Land coast. And the dots show the positions of these swift buoys that were deployed to measure waves and upper ocean turbulence during several deployments in May of 2017. And on the right-hand panel, you can see what the wind speeds were, the significant wave height shown in the second panel, salinity and ice thickness at this particular time. The ice thicknesses were measured just by visually observing from the ship with aspect observations. So basically, at wind speeds of 20 meters per second, which are not the highest winds that were observed in the Terra Nova Bay Polynya, we're seeing significant wave heights of up to 2 meters for this particular buoy that we for this particular buoy deployment. We also saw waves at some of the other locations as well, but this 5 May event was the largest one that we had seen. So how do waves in the Polynya differ from what's expected? And this is a calculation that Matty Smith did. And basically the colors indicate the time from deployment of the swift buoy from beginning to end, 0 to 12.4 hours later. And at the beginning, what we saw was that initially the waves were bigger than expected and then smaller at the end of the deployment. The end of the deployment was actually when the ice formation was getting larger. And so there was some attenuation we expect on that. The bigger at the beginning is probably a result of this particular calculation, which was done with the wind speed at the buoy and averaged over the entire fetch, when we know that the Cataback wind at that particular point had actually dropped off from about 30 meters per second at the coast down to about 20 meters per second where the buoy was calculated. So if we raise the wind speed up or took it in a tapered fashion from the coast out there, we probably have a better expectation of what the significant wave height was. In the expectation here, and it might fall better on the one-to-one line. The waves are also longer period than what are expected. As I mentioned, these are very, very high winds that we're seeing here. So, but basically, it's a wind, a local wind sea, if you will, generated by very, very high velocity winds. Now, this just shows some photographs of the wave conditions taken from the vessel as we were following the buoy, essentially. So initially we're seeing this formation of waves in the air with these bands of loose crystals of ice called frazzle ice. And then as time went on, we happened to see an increase in the waves in this particular time. And now if you look closely here, you can see there's a lot of breaking waves, and I'll allude to those fashions. And as this frazzle ice was forming, it formed in wider and wider bands, as we can see later on here. So we're seeing start the formation of these very wide bands of frazzle ice as some of these accumulated together. And eventually, as you can see in some of these structures, you can actually see the formation of the pancake ice. So we're moving downwind all the time in the traverse of this area here. And I think I'll stop this and move on now. Now, I'm just going to allude to the breaking waves and how we calculate them. It'll become apparent as to why I'm doing that in a minute. But basically, we have wave breaking formulas can include basic wave parameters computed in WAM, our previous wave model, such as the wave steepness, where you find all these parameters associated with, and with the energy density here and the frequency and direction of the domain. And basically, you can figure out the white capping that's doing that, which is a function of the energy density at a particular wavelength and frequency. So, and we can see, again, this is the hours that we're talking about. Early in the hours when the waves were stronger, we see a very high frequency component, and this led to those breaking waves, and the waves were generally attenuated later on as we get the high frequencies, especially as we're getting into the ice cover. So in the early part of it, we're seeing probably the highest formation of the breaking waves, and then later on, there's the high frequency waves are attenuated, and we're starting to see just a lower frequency component. So why are the breaking waves important? Well, it turns out to be important because of the generation of sea spray. This is a photograph taken there, and you can see this kind of high density of sea spray that we're seeing here. And I'll be talking a little bit about what that effect is on. It's basically if you have breaking waves and you have droplet formation, you can actually enhance the total heat fluxes. You have the interfacial heat fluxes, sensible heat, and latent heat. And then there's as the droplets are into the atmosphere, they can give up sensible heat again to the atmosphere and take on latent heat either by evaporation or by freezing. And so the total sensible and latent heat fluxes are in the upper atmosphere, or from the ocean to the atmosphere, are actually a sum of these. So when you have waves, you can actually have an enhancement of the heat fluxes. So Peter Guest has done some effective ocean surface freezing, and reduce sea spray production when you get wave suppression because of the formation of the liquid surface by sea ice. So he's calculated a sea spray production factor based on these various ice types, so that you have the highest production factor from sea spray with the open ocean. Grease and sugar ice, the frazzle crystals that I mentioned, have lower than, and then when you get into small pancakes, you don't have any breaking waves, you don't have any sea spray formation essentially, and thicker ice types, it's essentially zero. So here's a calculation, a calculation of the sea spray freezing effect. And you can find it. This is the traverse that was made down the Terranova Bay Polinia, and we find that there's about 200 watts per square meter that you can find from just from the freezing spray effect, and it drops off as you get into the ice cover further downwind in the Polinia. Here we can find that the sensible heat fluxes are contributing most of the total heat fluxes, and they're composed almost equally by the interfacial and the sea spray in this early part of the Polinia. So we have very high heat fluxes in this Polinia, much higher than have been measured essentially anywhere in the world ocean, and of course this leads to very enhanced ice production. The latent heat flux is not so much, so the total, the interfacial latent heat flux and the total are very similar. So just to take a look at the sea ice growth again, you can see the panels from that time lapse that I had, and you can see that we're forming, as we go further along in time, the pancake ice that are formed in that area. Now, if we take a look at the marginal ice zone, I'll just finish off with this. This is a photograph that was taken there. We have enhanced ice growth from the formation of pancake ice in the marginal ice zones. But these wave generators are not the local wind sea that we're seeing in the Polinias, but can be also from a long period swell that comes in from a farther region. So wave damping by ice in the marginal ice zone gives you the feedback between the ice and the waves. So we see that there's enhanced pancake wave attenuation, less so with grease ice and even less with open water. So how do we implement this in ice models? Basically, if we have open water, you have cooling, the rough water has to include these new effects of the sea spray and the enhanced heat fluxes that are there. And then you lead frazzle grease ice, pancake ice, and you get the new ice field evolving in that particular area. And so this is looks like a reasonable way to model the ice formation in these Polinias, where we can take advantage of the formation of waves and get these enhanced ice formation processes in the Polinia. In the marginal ice zone, we're going to need a coupling of wave and ice models and ROMs with ice oceanography and feedback into Wave Watch 3, because we're getting attenuation of these waves as they're going through. So we'll need both these types of models. So that's about it. I'd just like to thank you for your attention. Thank you.
Great, thanks, Steve. Looks like you've presented us with another modeling challenge, so that's always great. Does anybody have any questions for Steve? So Steve, while somebody's typing or whatever, I have a question there. So the inclusion of brine within the sea ice, is that generally happens during the transition from frazzle to pancake, from grease to pancake formation?
Well, the pancake ice forms that you'll capture some of the brine in there. Basically the frazzle ice is basically a slurry of ice and water. You will have brine rejection because the ice crystals themselves are fresh, and then there's rejection of brine in that. But actually, the incorporation of the brine into the ice has to take place when it's solidified into the pancakes.
Okay, that's great. Thanks, Steve. So very quickly, there's a question from Jay Vermans. Perhaps you can answer very quickly.
Yeah, I see the question. How was the sea spray measured here? Basically, it was just calculated what the total heat fluxes were measured, and then when the when the interfacial comparison of the heat fluxes was compared to the total, it was found that you needed to have that extra component from the sea spray. So the sea spray itself was not measured, but it's the actual formulation of the sea spray actually comes from people that were working in tropical cyclones, because they figured out that there was much enhanced heat flux, and it's a function of wind speed. And there's a theoretical calculation that's done on that, where you can associate the generation of the sea spray with the wind speed. So we're seeing very high wind speeds here, 30 to 35 meters per second. So it's basically from that formulation that you can calculate what the heat flux component is from sea spray.
Okay, great. Thanks, Steve. So we'll move on to our last speaker now. If you can unshare, and Andreas Klocker, who's our last speaker, if you can start sharing your presentation. Andreas will be talking about ocean ice interaction in the subpolar Southern Ocean, generating the internal picnicline. So Andreas, if you're ready, start. Andreas, you're still muted, I'm afraid. Andreas, you're still on mute.
Can you hear me now? But now I got to share again. How is that? Can you hear me? Am I good now, Will?
We can hear you and we can see your slides now.
Cool. Sorry, a brain fart this morning. It's too early for me. But yeah. So I'll talk about some ice-ocean interaction with subpolar ocean and how it generates the ocean's internal picnicline, or in more simple words, how ocean ice interaction with subpolar Southern Ocean generates the stratification you'll find in the ocean basins to the north, for those who don't like picniclines as much. So that's all work I've done over the last couple of years in collaboration with those characters mentioned below: Alberto Garabato, Casimir de la Verne, Fabio Roque, Steve Rintel, and Will Hobbs himself. Bit of theory to start off with, since I'm probably talking to more ice people than oceanographers. What is the permanent picnicline? By definition, a picnicline is a thin layer where a vertical gradient of density has a maximum. So it's a thin layer of high stratification or high density gradient. In the ocean, the permanent picnicline, ignoring seasonal effects right now, is a major organizing feature which kind of splits apart the relatively fast ventilated waters of the upper ocean from the more slowly renewed deep waters. When I'm talking fast ventilated waters of the upper ocean, think moat waters, and intermediate waters, think heat uptake, carbon uptake. When I'm talking deep waters, think circumpolar deep water. Now going back to some theory, if you look at some old kind of theoretical papers, you can actually split this permanent picnicline into ventilated picnicline and an internal picnicline, which I'll show in some model results where it's maybe a bit more intuitive. So in that ventilated picnicline, the wind-driven motion pretty much connects whatever happens with those isopycnous outcrops, those water masses, with the ocean interior along isopycnous. You set something in motion at the surface and it moves along isopycnals into the interior, transporting heat, transporting carbon, etc. But in contrast, the underlying internal pycnocline is actually an interface which develops at the bottom of this ventilated thermocline, creating a layer of very high stratification. So there's some caveats to all those theoretical papers from the past. First, they omit the impact of the Southern Ocean channel. Most of the things have been based on the North Atlantic, but it's been thought that that channel configuration leads to a very different pycnocline structure and the emergence of a vigorous overturning circulation. Second, something which is going to ring a bell with everyone working on polar oceanography, all those theories think that density is set just by temperature, but everyone who knows and works in the polar ocean knows that most of the polar stratification is actually set by salinity, and the nonlinear equation to component fluid stratification is crucial. So let's see what happens if we address those caveats and actually look what happens in a realistic model. For those modeling nerds here, I'll just quickly go through the model I use. It's a two-way coupled ocean sea ice model. The ocean model is MOM5, and I use the Los Alamos sea ice model on it. Those both ocean ice are forced by the 55-year Japanese reanalysis, and this particular configuration is run at a high resolution of 1/10 of a degree. So it resolves a good part of the mesoscale, and it has 75 vertical layers. And that's all run by the Consortium for Ocean Sea Ice Modeling Australia, or COSIMA, and there's more on that model on that webpage listed here, and there's a paper just been published describing the models in case you're interested. But here now, I show some examples of meridional sections of the main three ocean basins of PV and salinity. So first, all those bluish, whitish panels, the first one, the third one, the fifth one, are potential vorticity, which is here written as the Coriolis parameter times stratification. If you don't like thinking in vorticity terms, every time I say high vorticity, just think high stratification. The colorful lines are different isopycnals. I chose to mark particular features in a watercolor, which I'll explain in a minute. The orange line at the surface is the maximum sea ice extent, or what I'm looking here at time of 5 years. And the vertical lines show you the main fronts in the Antarctic circumpolar current, giving you an idea where we are. So have a look at the top panel now, which is the section in the Indian Ocean. So what you see right away are those black patches of very low potential vorticity. Those are the main water masses. Here in the top 800 meters is subantarctic mode water, for example. That's produced by deep mixed layers, which destroy PV, destroy stratification, and hence show up as those low PV values. Kind of similar but weaker, you see the Antarctic intermediate water below, and at depth, the circumpolar deep water with very low PV values. But in turn, the high PV sheets bounding the low PV layers define the fabric of the ocean's permanent pycnocline. So you see those really high, thin PV layers, which act as an interface between, for example, subantarctic mode water and Antarctic intermediate water, and Antarctic intermediate water and circumpolar deep water. And the interesting thing is here, so I chose those isopycnals to align with those internal pycnoclines. And what you see is that both the PV values are strongest in the subpolar Southern Ocean, and in the subpolar ocean, they deviate from those isopycnals, pointing towards frictional and diabatic effects working on that PV. Whereas in the interior, PV is pretty much conserved. So you see this pretty much exactly the same happens in the Pacific section. And I'll come back to the Atlantic section a bit later because it's more different and more complicated. So what I'm going to show on the next figure now is this Pacific section, so the third panel here, but zoomed into the subpolar Southern Ocean and focusing on the top 300 meters. So that's what you see in the top 6 panels here. So before I show the temporal mean over 5 years, here I show the seasonal evolution starting in February and then showing 2 months later, etc., until December. Colors are exactly the same. The green and the blue show the isopycnals associated with the internal pycnocline. Orange on the surface is the sea ice distribution. In the second panel from the bottom, I actually show temperature. I mainly show this panel to show where the circumpolar deep water just here sits very close to the surface. And the line plot at the bottom shows the freshwater fluxes from sea ice for those different months. So what you see if you focus on the top panel, the highest values of PV or stratification in summer are right at the surface where you get ice melt a freshwater lanes and huge stratification. If you move down the panels towards winter, now you get cooling and mainly brine rejection, slowly deepening that pycnocline and slowly eroding it away. By the time you get to June, you see that the seasonal pycnocline is almost gone. So intuitively, you would think this would continue on and kind of erode away that permanent pycnocline, which here in June is associated with that blue pycnocline. But what happens particularly here between about 69 south and 73 degrees south is that we have that warm circumpolar deep water sitting very close to the surface. So if we have brine rejection trying to deepen and destroy that permanent pycnocline, we actually start mixing up warm circumpolar deep water, which warms the surface layers and starts melting ice. So we got a feedback first described by Martins, and I think it was in 1990, which actually stops the sea ice production there. So we start producing ice, we get brine rejection, we make the water warmer by mixing up warm water, and we actually melt ice. The interesting point here from an oceanographic point of view and a large scale thinking point of view, we can actually get circumpolar deep water up from depth to the surface while maintaining this strong pycnocline. If you would destroy this pycnocline here, we would not see the same stratification to the north, which we do in this model. A bit further to the north, we see that the mixed layers never get deeper than this permanent pycnocline, and we can't really reach the warm water reservoir below. And then further north, the ice just melts because we hit the ACC. You see that aligns with what we see in the freshwater fluxes. In the far south, we get a lot of brine rejections and negative values here where ice production happens. Where we got the circumpolar deep water, the values are pretty much positive all year long because we are mixing into the warm circumpolar deep water. And below that, north of that, we actually get positive and negative values. We get freezing and melt. And at the far north, we always get melt with the ice kind of being pushed in the warm ACC, producing a high PB layer. Let's have a look at what that looks like in the horizontal case. So that magenta line is the section I just showed. And here I showed different properties at a depth of 120 meters. The top handle is potential vorticity, or again, stratification. Second is temperature. Third is salinity. And what you see already here is that the highest PV values are in the places where this warm and salty water comes close to the surface. What you see in the fourth panel is what I call stratification ratio. I'm not going to go into details now, but everywhere where you got those very yellow patches are areas where the ocean stratification is strongly set by salinity. If temperature would be setting stratification, we would be unstable. So the bottom here, I show again those freshwater fluxes at the surface for the month of July, so in winter, and you see that those regions of high stratification or low stratification ratio, where the circumpolar deep water comes up close to the surface, we also get melting of ice in the middle of winter. So that shows you what I showed in that one meridional section actually happens around the ACC. So here I'm back to the figure. What, 5 minutes? Okay. So here's the same figure I already showed before, but there's a few different things I want to point out. So I showed you guys how that ice-ocean interaction in that salinity-dominated subpolar region actually can maintain very high PB while getting a circumpolar deep water up. So now if you look further north and look at the ACC fronts, here in olive, the southern ACC front, and in white dash, the southern Arctic front, it is these ocean fronts where that internal pycnocline leaves the base of the winter mix layer and actually dives into the ocean interior where it's protected from any further surface forcing. If you wouldn't have those fronts there, we'd probably get a way more homogeneous water mass distribution in the interior. The other thing is now, if you look at the Atlantic Ocean, you see again, there's a very high, strong pycnocline associated with that magenta isopycnal and the cyan one, which is at different densities, at lighter densities than in the other basins, which is interesting. I don't fully understand everything yet. The difference between the Pacific and the Indian is, in the Pacific and Indian, the Southern Ocean can do what it wants, because in the North, you just have some passive puddles, because there's nothing much dynamically happening. Whereas as soon as you go into the North Atlantic, you have ice-ocean interaction up there. You have deep water production there. So the Southern Ocean, the North Atlantic actually have to communicate with each other. So there's a reason why they're quite different, but there's still quite a few things I don't understand. So one more figure here that shows the zonal evolution of PV. So before I showed meridional sections, now I show zonal sections, and focus particularly on the bottom two, taken at 45 degrees south and 41 degrees south. You see an internal pycnocline following this green isopycnal in the Indian Ocean, which is far left, and the Pacific Ocean, which is in the middle in both those figures. So those internal pycnoclines are pretty much isopycnal. But once you go downstream, so from left to right past Drake Passage, which is this white masked block here, you see that they suddenly jump and follow lighter isopycnals in the Atlantic Basin. So there has to be something really exciting happening in Drake Passage, changing the internal pycnoclines from that green density to the magenta density. There's still a lot there that I don't understand, but it's really exciting stuff, I think. And I'll leave it here. Just put the take home message on there. But in simple words, if there's one thing you got to remember, is that the subpolar Southern Ocean, with its salinity dominated stratification and ocean ice interaction, really sets your stratification far towards the north and not just locally. That's it.
Great, thanks for that, Andreas. Interesting stuff. We have just a couple of minutes for questions since we started Andreas a little late. So does anyone have a question for Andreas? If your typing is as bad as mine, maybe it's better to just chip in. Okay, so Andreas, I have a question while we're waiting. So you said that with brine rejection, you're able to mix up the warm circumpolar deep water into the mix layer without necessarily destroying the pycnocline.
Yes.
Could you explain that? Because that's pretty interesting. Could you explain that a little bit more detail?
So from an overturning point of view, you've got to have a volume transport from that circumpolar deep water to the surface to close your overturning circulation. So you somehow got to get water parcels across this pycnocline. So if, in the most simple case, you look at outcropping isopycnals, you get your circumpolar to the deep water to the surface, transform it, and it sinks again. That's what you kind of see in classic channel models, but that would not give you a permanent pycnocline because it would pretty much destroy this stratification. So this negative feedback kind of lets you get that volume transport of circumpolar deep water to the surface, but because right away after it leads to a melting of ice, it kind of generates or maintains, I should say, this pycnocline, if that makes more sense, or it's more confusing.
I'm going to have to think about that a little more and after another coffee, but that's great. Thank you very much. So I think it looks like that brings our session to an end. We'd like to thank all the speakers again and to everybody who's dialed in at times both convenient and inconvenient. I think it's been a really great session. We're sorry we couldn't host you here in Hobart, but I hope that everybody has enjoyed it and found it useful.
Can I just add one more thing? Can you all just unmute and say something so that everyone who's listening to this will realize that there was a huge audience out there? Just say anything.
Well done, everybody.
Thank you all.
Thanks, everybody.
Thank you.
Bye, everyone.
Thank you.
Bye.
Thank you.
Thank you so much.
Thank you very much.
Thank you.
Thank you. Bye.
Thank you. I'm now going to stop recording.